Okay. Hello, everyone. Welcome to day 2 of AKBC 2020. Today, we continue a set of 5 speakers and the spotlight papers, as well as poster sessions, followed by hallway discussions at the end, similar to yesterday. So now it's my pleasure to introduce our first speaker today, Luke Zettlemoyer. He's a professor at University of Washington and a research scientist at Facebook AI Research. Luke is a leader in natural language processing, including many different areas, especially most recently on self-supervised learning representations for NLP. You probably have known some of his recent work, especially like Elmo, Roberta, BART, and many other Sesame Street characters. He has received numerous awards, such as a Presidential Early Career Award, Ellen Distinguished Investigator Award, and several Best Paper Awards. So, Luke, please go ahead.
Thank you, Hannah, for the wonderful introduction. Thank you to all of the organizers for inviting me. I think this is a really fun venue to talk about pre-training work. I have to admit a little bit in advance that there's nothing actually about knowledge-based population here, but I still hope that the models will be, very relevant to what everybody's thinking about. This is joint work done between Facebook and the University of Washington, although a lot of it is done at Facebook because it's a reasonably large scale. I'll have a slide at the end where I really thank everyone that was involved. There's some pretty big teams in doing these kinds of projects, but I wanted to highlight the names here of people that led some of the projects, and especially Mike Lewis, who not only has been doing a lot of these models, but actually made the slides that I'm shamelessly stealing and using today for the talk. Okay, so if you think about pre-training these days, then probably the first thing comes to mind is scale. So we're going really big scale and things are getting much, much better. And here's a figure that I stole from the GPT-3 paper that came out very recently that I just think they did a really nice and beautiful job of kind of framing this scale. So if you look across the different colors here, green, purple, blue, these are kind of different self-supervision signals, maybe a math language model, maybe a causal language model, so forth. We'll talk about that later. Across the x-axis, things are roughly getting bigger within each bucket. But the really interesting thing to focus here is the y-axis. So you see this is a log scale. So we're really, the number one factor that's really determining how well these models work overall is, just how much compute you pour into them, okay? But the tricky thing is that comparisons are hard and details change. And, it's sort of, we just kind of know that scaling's happening, but I don't think we understand that well, like exactly what tasks and exactly why, like which subdivision works better and which doesn't. So in this talk, I'm gonna actually do something different. I'm not gonna focus on scale. Okay, and instead I'm going to focus on new tasks and new kinds of self-supervision signal. So the implicit assumption here is that scaling up will always help, but what we would like to do is understand, within a given scale, roughly, and I'll try to be careful about this as we go, roughly within the scale of Roberta here that we did at Facebook, what actually helps most and how do we expand out so we can do pre-training for more and more tasks. Okay. And just to give a little history to kind of think about how to frame all of this, of course, pre-training is not a new idea. We have these wonderful pre-trained word embeddings, but here we have a single vector for each word. They're in very wide use for a long time. And actually, this is at a much bigger scale even than we're doing for a lot of the pre-training methods today. So just think tons and tons of text, but a pretty lightweight model. And then, a few years back, we showed that, actually you should not just have a single vector for each word. We should really thinking about the meanings of words in context, different vectors for different contexts. And, then, of course, we were still in that mindset of word embeddings, but, other folks came along and said, actually, no, what you should do is you should pre-train whole architectures. So this great line of work, one of those little buckets I showed you there was they show that it can work for lots of different tasks, but it's really unclear. Is that the right architecture? Is that the right objective? Is that going to do the best for all the different tasks? And then, of course, we all know about BERT. They don't need to say much here, but the idea was they kind of built on GPT. They introduced this masking objective. It was able to be bidirectional, and you can get much better context for each word, and kind of, then basically the field reset, at least in terms of lots of modeling, right? And, again, a shamelessly stolen slide from some folks that I found on Twitter. there was this huge explosion after that. And everything started branching in lots of different directions, a lot of really amazing work. And to set the context for this talk, what I really want to do is focus roughly in this area here, if you can see my mouse, roughly the kind of sticking just with plain text, but trying lots of different signal, lots of different tasks, moving from, for example, discrimination tasks to also include generation tasks, thinking about different ways of using these models and so forth. So that's the part of the space we're going to talk about. But my hope is that we'll also be able to be a little more careful about experimentation and measuring things, and that sort of the methodology that we adopt would be useful more generally to try to carefully control for exactly what's going on in these pre-training schemes, exactly what's working and what's not. Okay, so to go a little faster, just to set the stage, okay, we one of the projects, the first projects we did in this direction, we were trying out lots of different objectives. We were trying to replicate BERT. And so we did this for BERT project, and that was really kind of came out of the idea that there'd been so much going on, and actually some of these objectives we had even tried ourselves, and in careful comparisons, we didn't find much gain. And so we were a little confused about some of the reported results. And so what we said is, what if we just take BERT, we just add more data, we just more carefully optimize it, throw more compute at it, what would happen? And roughly speaking, the actual tasks here are important. I'll get more into tasks later. But roughly speaking, this was the original gain from blue to green here of BERT, and there was, easily that much gain again if you're more careful and you optimize better and so forth. Okay, so when you see this kind of result, you can ask yourself, are we done? If we just let BERT keep training and throw more data and more compute at it, is NLP solved? Right? It's a little bit intentionally controversial here. I don't actually believe this. Well, actually, if you're careful enough to scope things, so if you look at English, you look at classification tasks, and you look for tasks for which you have a lot of data to fine tune, we're getting superhuman performance. Maybe, of course, we have all these data set biases and stuff, but it's tempting to think that maybe that's true. Rather than trying to, actually answer that question, what I want to do in this talk, I'll leave that for others to debate with each other. What I want to do at this talk is actually go in a different direction and say, how do we go in new directions? So how can we generate as well as classify? Within a generation scheme, how do we go to other languages? And are there other fundamentally different types of self-supervision beyond language model and word masking that can really change how we do pre-training? Okay, so that's what the talk is going to be about today. All right, so to set the stage again, remember that masked language models are working really well in classification. I didn't say it before, but if you do pre-training of a causal left to right language model, you can get really impressive generation out of it. We've all seen the online demos. And the BART model, the model that we developed, was an idea of sort of how do you get the best of both worlds? So how do you get an approach where you can get some bidirectional component, some autoregressive component, and fit them together? And hopefully that such a model, if you can figure out how to pre-train it, will be good for both generation and classification. Okay, and Mike Lewis, who is really running this project, came up with this really clever idea that's sort of technically so simple but very general. And the idea was, well, actually, we know architectures that can do this. Machine translation architectures can do this. They have an encoder and a decoder. And what if we just do pre-training basically as taking, say, an English sentence for now, doing any arbitrary noising you want to it, that could be masking, that could be something else, creating a corrupted version of that sentence, and then training a machine translation model that can translate that corrupted version back to the original. Okay, and that's the whole idea. I mean, it's really simple. It works really well. But that's the BART pre-training approach. And the cool thing now is that we can have an arbitrary noising function. So we can do any kind of noise we want. And it will allow us to kind of run more controlled experiments of, what if you mask this way? What if you do this other thing? Compare them to each other. What kind of noise actually works? Okay, so in addition to getting more tasks, we're getting better understanding of what works. And we've had a really fun time with this project, kind of thinking about all the different ways that you could do masking. So for example, or you could do noising, excuse me. So for example, you could do token masking. So if your encoder, gets basically what you're feeding into BERT normally, and you decode the original full sequence with those masks filled in, that would be one way of doing noising and translation. Another option, maybe you don't want to mask, maybe you just want to delete tokens. So you could say, well, I'm just going to have this shorter input, and I'll have to recreate not only what's missing, but where it's missing from to create the original thing. you could rotate the document. So here we've just taken the string and shifted it. One thing that you can notice with these examples is I put periods in there because in general, these are pretty big chunks of text. So although we often think about NLP at the sentence level, I think it's better to think about this as a short document than an actual sentence. And then, with that in mind, you can also do sentence permutation. So maybe you can get more discoursey effects if you take all the sentences in a document and randomly shuffle them, feed that into a model and ask it to sort out what the original text was. Okay. And then the last one that we tried, and by no means this list is exhaustive, but this is just things that we were able to experiment with. I think there could be many others. But the last one, and spoiler, the one that's going to actually work the best is the text infilling. So here, this is like a generalization of BERT and span BERT. So the idea is you take spans of text that are sort of Poisson distributed. And what you're going to do is remove the entire span, put in a single mask, and ask the model to recreate it. So it needs to kind of reason about how many words are missing. It needs to fill in the blank. And you can also use zero length spans. So that gives you a little bit more flexibility. Okay. And I think this would, if I could pause for questions, this is a place where I'd like to do it, but you can ask me some afterwards and we'll come back. But the basic idea here is that we have a lot of flexibility and we could have tried many other things, but we did sort of what we thought was reasonable at the time. Now, as I was alluding to earlier, and as this beautiful picture that Mike found shows, I think it's maybe a little bit cartoony, but actually fair to say that the comparisons in the pre-training literature are Wild West. If you look carefully at the papers, the amount of pre-training compute, the actual data involved, the hyperparameter settings, they're wildly different from every paper. So I think as a community, we can say we know we're making progress, systems are getting better and better, but I don't think we have the best idea of exactly, why or how, like exactly what factors contribute the most. So one thing that we want to do here is a really careful study of that. So not only are we going to look at those different noising schemes that I just went through, but Mike amazingly also went and re-implemented in a similar framework a bunch of other models that had been published at the time so that we could compare different noising schemes with different published models. There's a slight caveat here that it's hard to replicate the models, so they'll be in scare quotes to say we did the best we could on that replication. You can see the paper for full details, but they're pretty close and I think they're representative. Another caveat is that we did this kind of at the BERT base scale, one of the smaller bars in that first slide I showed you, just because of the massive amount of compute involved. We don't know for sure that the trends will hold at the larger scale. I think there's reason to believe they might not, but it's still sort of the best we can do right now. And that's, I think, an open challenge in this work. Okay, so let's look at some numbers. So for QA, what we can see is that masking and deletion, so at pre-training time, actually removing a phrase and having to put it back in, whether it's a word or a phrase, this is really crucial. And that kind of treats the model basically learns how to represent spans and intuitively learns what answers to questions looks like and learns how to deal with that. Crucially also here, if you look at the bars that are lower, where lower performance is bad, this is accuracy. These are more things that don't have that masking or more traditional language models, and they just can't really build such good representation context, for example, if they're left or right. If we look at generation tasks, we see basically the opposite trend or a similar trend, but actually it's helpful to have some amount of seek-to-seekness to the model. So if you're just doing masking, it's kind of hard to generate from those models. And here, this is perplexity, so lower is better. And what we're seeing is that if you have some amount of masking, some amount of bidirectional context, and also some ability to generate, then for tasks like summarization tasks, that seems to work really quite well. Okay, so that you can look at the paper for more details. That's just a vignette of some results there at that smaller scale. Of course, we also want to see how does it work at a bigger scale. And this is kind of the Roberta scale. This is not as big as these other models, but with a reasonably diverse data set of text. And one cool thing that we found is this Roberta model, which is very discriminative, can't really do generation. BART is able to match it, essentially just lag a little bit on a diverse set of different classification tasks where you might expect BART to struggle. And that we're able to set new state-of-the-art results. So here is a comparison with some baselines and previous more generation-focused pre-training approaches. for roughly speaking, an extractive summarization task. So it's one where you don't have to do as much inventing of new text. And so we get a little bit of a bump there. But where it really shines and where we get the biggest gains are on more abstractive summarization, where you need to kind of really be creative and come up with rewordings and synthesize things from all over the place within the input text. And there we're seeing bigger gains over the previous work, although admittedly it is a less studied task. We also did some human evaluation, and we found that humans prefer BART to the previous baselines to the previous state-of-the-art models quite strongly, and even sometimes prefer it to the human references, although not that often. Definitely humans are doing a better job of summarization than BART at this point. There's still a lot more work to be done. To make things a little more concrete, here's an example. So this little story here that we want to summarize is about a diplomat's wife and an unfortunate situation where there was an accident, and they're kind of debating whether there's immunity and whether they can, get that diplomat's wife to come back home. So BART comes up with this really pretty, I think, very impressive summary. Boris Johnson has said he's raised the issue of U.S. diplomatic Sokola's immunity with the White House, roughly. Okay, and just to highlight some things that went really well here. We had some interesting co-reference patterns. So to figure out who actually said this thing, you actually need to combine information from all over the document. Who knows if the model is actually doing that latently or picking up some other factor, but it's in the final output, both for the entity and for the event. Also some encyclopedic knowledge. So the first name of the prime minister was never actually said in the document, but somehow is able to still create that in the summary. And actually, one scary thing with the pre-training for these kinds of things is that they can sort of hallucinate or stick in extra information or get something wrong. And so, one interesting thing here is that this person is not the diplomat. It's the diplomat's wife, but the summary is very confident, or there's no confidence here, but the summary, gets that wrong. And on first glance, if you were reading it, you may not even notice that. So it could even, be bad in lots of ways. Okay. So that's the summary for the BART part of the talk. Seek-to-seek pre-training by kind of arbitrarily noising and translating back to the original. Put a lot of effort into these systematic comparisons. The fact that span masking works is not a huge surprise given what else was going on in the literature, but the fact that it can be integrated into a generation approach, I think, is quite nice, and it works well for generation and classification. Okay, so what I want to do now is, with the remaining time I have, I'm going to talk a little bit about other languages. It's specifically in this generation framework, so I'm not going to talk about mBART and XLM and those models much, other than comparing performance to them. But I'm really going to talk about, within this BART framework, how do we get other languages in there? And then, how do we go to more general sources of supervision for training these seek-to-seek models? So, how could we go beyond English inputs? Okay, so when we have BART, one way of thinking about what we have here is, a big model that's pre-trained to take, noisy English text and produce beautiful, clean English text, right? That's how it's pre-trained. And so one thing that we did in the original paper, just to kind of understand how general this is we did this slightly funky thing where we said, okay, what if you wanted to do translation? So you could take some input sentence in a foreign language, run it through an encoder. Think of this as like a non-autoregressive MT model down here at the bottom. And all that decoder needs to do is get you to some noisy English. Okay, it's got an easier task than a normal MT problem. And from there, we'll rely on BART's pre-training to sort of take us the rest of the way and clean things up for us. Okay, does that make sense? So you can do this in two ways. You can fix the parameters of BART, and given an MT corpus, you can backprop all the way through those fixed parameters and only estimate this MT part of the model. Or you can do some of that and then loosen things up and allow everything to fine-tune together. And what we actually found is that, compared to a strong transformer seek-to-seek baseline, it does work in the fixed approach. BART is able to do that. And then if you tune it a bit more, you get some nice performance gains about a blue point. And so this is kind of giving us a different way of getting monolingual target text into MT systems than, say, back translation or things that people commonly do in practice. And I don't know if it will take off for that reason, but it also just shows that BART is very general. I mean, you can train whole other models just by popping through it, which I found really pretty fascinating. Okay, and when I said multilingual, what you probably thought I was going to say is this next approach. So we had a whole follow-up paper on mBART. And we sort of did the standard trick for corpora in different languages. You treat it as if it was all just one corpus without any sort of special handling, and you just train a BART model on the concatenation of all that text. Okay. It turns out this just works really well for MT. You don't get huge gains in the high resource case. In general, for pre-training, it's not going to help when you have tons of label data for your end task, or at least not as much, but it did help a lot in the cases, in the more low resource or mixed resource cases. Here's one example of a whole bunch of different, I'm sorry, here's a graph of lots of different language pairs, and this is sentence level machine translation. And you can see, compared to a random initialization, that a mBART model trained on 25 languages gives very consistent gains across all the different cases. Okay. And then, the paper has just tons and tons of experiments. I encourage you to go look if you're interested. But another thing that you can do that's kind of unique to mBART, because it's pre-trained on all these languages at once, you can fine-tune on one X to English pair. So for example, you could fine-tune on Chinese to English. And then you can test on some other pair, say Italian to English, without ever having seen Italian by text at all. Okay, just because of that joint embedding space that you get from the pre-training. And this is big matrix here from the paper is kind of showing you what happens. And you get kind of, of course, the best numbers on the diagonal where you're not actually doing this transfer across languages. But within related language families, you're getting some really interesting behavior, and sort of, in general, you can get this kind of zero-shot performance. And again, I don't know this would be the most practical way to build an MT system, but it sort of says something about what we've learned within mBART, that it actually has some interesting behaviors, but not in every case. It's sort of not perfect, and it's kind of interesting to look at that more in the future. Okay, so that's a little foray into the multilingual case. And now what I want to do is talk about actually a paper that is not yet out. So I'll give you an early preview of our newest seek-to-seek pre-training approach. We hope to have this on archive within the next few weeks, so you can keep your eye out for more details. And what this approach is another Simpsons character called MARGE. And we think of this as pre-training via paraphrasing. So the basic goal here is to still think of pre-training as denoising autoencoding. We're going to take some text, we're going to get some noise, and we're going to unnoise it. But we're going to think of fundamentally new noising approaches. So in the first part of the talk, we tried all kinds of noising, and we end up at a mass language model, which was great, but maybe a little disappointing. Can we get beyond mass language model and think about fundamentally different ways? So the way the noising is going to work here is that we're going to take a document, and we're going to do two things. We're first going to run a retrieval stage. So we're going to have a model that we can use to embed documents. And we're going to go out and we're going to retrieve documents across a huge corpus that we think are paraphrases of this document. And crucially, these documents actually can be in any language. So they don't have to be in the same language as the original document. And then what we're going to do is, given that set of documents, throw away the original document and say, now write a story by piecing together information across these different documents. So you can think it's a little bit like multi-document summarization. So given that we've retrieved this document, the goal is to reconstruct the original document that we already have. Okay, so I hope that's reasonably clear. And there's sort of lots of details on how you set this up, but I'll just give you a few little hints, and then you have to wait for the paper to get all the details. So the first retrieval step, the goal is to get a comparable document of some sort. It doesn't need to be perfect. It can be noisy because you're going to have this set of documents. And hopefully you'll get different information from different documents. So the bold here is showing you like maybe this first document you get gives you that part of it. This second document gives you some other part of it. And you've got some documents, some other language that maybe has some other coverage. Don't even have to have the same character set. And what you're going to want to do then is, in aggregate, the goal is to get enough information in a noisy way that you'll be able to reconstruct the original document. And one sort of fun fact here is that we're going to be able to learn to do the retrieval and the reconstruction jointly. So it's going to be a seek-to-seek model. And the parameters of the encoder will also be used with a simple pooling to build a document embedding that will be used for retrieval. And a really fun fact, actually, just to get a little bit on a tangent, is that randomly initializing that retrieval model is sort of like randomly hashing all the words in your vocabulary, and actually gives you a pretty good starting point. You can bootstrap the whole thing from random initialization. Okay, that's sort of surprising but fun. With one caveat, and the one caveat is that we actually limit the documents. We put them into groups, and we limit them to be published on the same day. So that actually helps quite a bit with getting paraphrases, because there's a lot. Think of this as a lot of news stories, and people around the world are discussing the same topics around the same time. Okay. Now we have this set of documents. We need to actually reconstruct the original. The approach here is actually a pretty straightforward generalization of what you saw in the first part of the talk. And you can just think of it as a many-to-one machine translation problem. So you're going to have this encoder. You're going to run it separately across all the different documents. And then you're going to decode the original document. And there's some details about how we actually set that up. We're going to rebalance things a little bit so that the retrieval model has some say in the reconstruction too, but I won't go through those details, and I'll point you to the paper for more information. Okay, so one way of thinking about this, actually MARGE pre-training, which we're very excited about going forward, is in many ways is actually kind of closer to end tasks. Like a mass language model is, it makes a lot of sense, it's well defined, but it seems very different than a lot of the end tasks we want. But this task that we've designed here, this kind of multi-document noising strategy, it looks almost exactly like multi-document summarization. And if you just look at one of the documents, it's a lot like machine translation. And there's actually an information retrieval component in it too, because you need to find the right documents. And there's a paraphrase component. And so maybe in general, a path forward for pre-training is to be kind of closer to the end tasks we care about, and sort of designing different ways of doing this noising and different things. And so we have a little bit of evidence. I don't think we've really proven this is the right way forward, but we can show this works really well. And at the scale we were able to do it for this project. So let me talk you through that now. And so maybe in general, a path forward for pre-training is to be kind of sort of getting some feedback. Anybody else hear that? Okay, awesome. So we evaluated a bunch of different things. So here we can see a bytext mining task. So in many ways, this is kind of closest to the pre-training signal. So I give you a sentence in one language, and you need to go find a sentence in another language from a large web corpus just by embedding them and doing nearest neighbor. Here we're comparing only to unsupervised techniques. So you can do supervised training with MT-Corpora for this task and get much better numbers. But this is really more of an exploration of what we've learned with the MARGE model. And we see, even compared to something like XSum, MARGE is trained again roughly at the Roberta scale, and XLMR you could think of as being kind of 5 times bigger scale or something. And even though we're at a different scale, we're using much less data because we're retrieving documents and so forth. We're able to actually, because the pre-training task more closely relates to this, we're able to do really well. Similarly, you could do cross-lingual question answering, where you're kind of training in one language and testing in another language for QA. And here we're lagging a little bit behind XLMR, but we still feel like this is a pretty strong result. And then you could also look at things like multilingual paraphrase detection. So, can you get paraphrases in lots of different questions? And again, this is very closely related to the task that we're interested in. And we find that the model is working really well, kind of tying with XLMR or maybe edging it out in some cases. Okay. And the final thing I'll note is like one really cool thing from this model is that, given the way you did the pre-training, you can actually test on document level MT with no fine tuning at all, like nothing. Just give it a document in one language, ask it to produce a document in the other language. I didn't mention, but at pre-training time, you do give language IDs for all the documents involved, so the model is able to do this. And these are just different directions. And shockingly, it's got a little bit of variance, but it's always a pretty good MT model. I'll show you some examples in a second. And sometimes, it's really quite good for some language pairs. So this is kind of towards the end of the talk. I just show a few examples to finish it up. But I'm not showing you the input source here, which was in German. I'm only showing you the English reference and the zero-shot unsupervised translation from MARGE. And it's getting a lot of the information. It's not perfect. But this model never saw any bytext at all. It was just trained with this kind of joint retrieval and noising. Okay.
I just want to give you a 2-minute warning.
Okay, I'm almost done. I'll be an extra minute for questions. And here is Arabic, which is really cool because, for example, it's a completely different script. Nonetheless, it's actually learning to do quite well. And Chinese, which I think is also quite good, although maybe you could argue a little bit less based on this anecdotal evidence. Okay. So that's kind of my story. To summarize MARGE, this I think is one of the first really effective pre-training approaches that's really fundamentally different from the masked language model, and we hope it will open a new direction of exploration. We're doing all these different tasks. They're somehow done a little bit jointly. And you get the zero shot and transfer learning opportunities. I don't have a slide on future work for MARGE, but it's sort of scaling it up as an obvious direction and sort of some interesting open questions there about how to best do that. To summarize the whole talk, we've talked about pre-training seek-to-seek models specifically. Turns out, you can, these are the very best at generation, and they also do well at classification. And where our focus really was on new tasks and new self-supervision and trying to understand what's going on, with a focus on these two models in particular. And here's the list. These are big team projects. They take a lot of work. And so I really want to make sure that I thank everyone that worked so very hard to get these things out. And I think that's it for me. And I'm happy to take questions at this point.
Thanks, Luke. A very great talk. So I have a lot of questions here in a Slido. So I am reading them according to their votes and popularity. So
and also, just because I forgot, I will definitely be at the chat this afternoon. So if we don't get to any of the questions, people can ask them then too.
Awesome. So first question, for these large pre-trained models, how could we diagnose or debug, say, when the model generates a biased, a factually incorrect prediction?
Yeah, I mean, this is a really hard question and one that I find really fascinating. One thing we're doing in a completely separate research project at Facebook right now is just trying to even measure it. So you could call this kind of hallucination. It's kind of inducing facts that aren't in a reference. And it's really hard to know, like, did a model just paraphrase or did it hallucinate? Did it go off the rails some other way? And so I think that we need fundamentally new tools. And I don't really think of this necessarily as, I mean, it's really crucial for pre-training, but I actually think it's more general. So like if you do MT systems and then you test them out of domain, even if they weren't pre-trained, you see really similar kinds of issues where they'll go off the rails and do strange things. So I think the first step is to like think about how to even measure that and get a metric for it. And then I would love to think about model design that could provide some guarantees, but there's a lot of work to be done.
Thank you. Second question, given impressive zero or few shot results from GPT-3, why do you feel pre-training can't solve everything? How would you characterize problems that can't be solved?
Well, that's a great question. Maybe I didn't do the nuances quite right on the talk. I'm definitely putting a lot of weight behind pre-training as being a really important direction. I suppose that, if you forced me, I can't. Hard to think of a task where it wouldn't help unless you just have a lot of label data and you don't need it. The GPT-3 results in particular are super cool. But I guess overall, I think that probably fine-tuning is always going to work a bit better. You're just going to get more supervision that way rather than the few shot, although the few shot is kind of interesting of its own right. I probably missed some of the aspects of that question, but that's kind of my thoughts on the area.
How do you compare BART with T5?
Yeah, so I thought about adding some slides, and I thought I would just leave it for the question. So thank you for asking. It depends on the task. At a comparable model size, BART is often performing better than T5. But of course, T5 had a really, really wonderful contribution in scaling up, and they did a lot of the really clever stuff there. And I think, we didn't go that route. And so, I think they deserve a lot of credit for that. I think scaling up is really interesting. So I think if you want the very best performance, then you should go for a big T5. But if you want something that works quite well and is at a more manageable size and easier to work with, then I think you're going to get much better performance from BART. Other than performance, I would also say that they were sort of done at the same time. And one key difference is that BART recreates the entire sentence, whereas T5 kind of masks the phrase and then just recreates what was masked. And I don't think we really understand that trade-off very well. I wish we could have included T5 in our careful comparisons that we did, but it kind of came out after we had done that. probably we should go back and do that and try to understand whether that difference really matters or not.
So I think I have time for one last question. How long does it take to train BART?
So let's see. I think that it's about less than 2 weeks, about 10 days, but it's on 256 GPUs.
Awesome. Thanks, Luke. I'm going to email you the rest of questions, and people can also ask the questions in the hallway discussion.
Thank you.
All right, I think it's time for us to move on to our next invited speaker. So it's a pleasure to introduce Dapa Nakashole, who is our next invited speaker. Dapa is an assistant professor at the University of California, San Diego, where she teaches and carries out research on NLP. Prior to being a professor at UC San Diego, Dapa was a postdoctoral scholar at Carnegie Mellon, and before that, she received her PhD from Saarland University and the Max Institute for Informatics in Germany. And today, she will talk about text processing for learning and automation of data science. Welcome to AKBC, and please take it away. Thank you.
Awesome. Can you see my screen?
No, it's blank.
It's blank.
We could see it earlier, but when you went full screen, we can't.
How about now? Oh, let's see. This depends. How about now?
No.
No? Oh. Stop share. Let's see.
I usually go full screen first and then share. That sometimes helps.
Okay. Let's see. Let's see. All right. How about that?
It's still blank, unfortunately.
Oh no, I don't know what is going on here. Let's see. This is shared window up front.
Yeah, maybe going back to the before presentation mode would work.
Before presentation mode. No. Screen. How's that?
Yes, this is working.
Okay,
Yeah.
awesome.
You're muted.
Hi. So sorry about the delay, and thanks, Ndapandula, for the introduction. I would also like to thank the
the hosts, the organizers, for inviting me to speak here. My first AKBC was about 8 years ago when I was a student, and I greatly enjoyed it. So being able to come here and speak is just such a great honor. So what I'm going to be talking about today is work we are doing on the topic of text processing to support data science, where by data science here, we simply mean it's the broad field of using scientific methods, approaches, and techniques to extract and glean information and knowledge from data. And this work is joint work with my students, PhD student Yutong Xiao and undergraduate student Yihan Wang. And the work we are doing on this topic actually falls under two themes. The first one is how we can leverage text processing, and including machine reading, for the task of supporting learning of techniques and approaches that are relevant and are important for data scientists to know. So for example, probability theory is one such example. And the second theme is about how we can leverage text processing and machine reading to automate mundane tasks, tasks that data scientists have to perform, but might not necessarily be super engaging. So for the purpose of this talk, I'm going to focus on the second aspect, and I'm happy to talk about the first one as well offline during the hallway conversations. Right, so our goal here is the following. So we want to use text processing to automate mundane tasks. So this is the second theme, as I mentioned. And the goal is to have an agent that performs actions based on user requests in natural language. And this agent is going to have access to documents and a knowledge base, basically information on how to perform the tasks that satisfy the requests of the users. So here I have an illustration where we have the user is a very responsible user, is wearing a mask, and the user issues natural language instructions to an agent. And that agent has access to some knowledge in the form of free text as well as a KB. And the agent learns or figures out how to perform the task based on that information. And then the agent performs the task and carries out some action and returns the result. So that is the goal that we want to execute here, have natural language instructions from the user, and then the agent performs some appropriate action. So let's consider one specific task that we as engineers and scientists are familiar with, which is the task of plotting. So plotting is a method that allows us to visualize data and functions. So for example, I might want to visualize the number of COVID-19 cases that have been confirmed for California or the US, or I might want to plot some functions. And for plotting, we have useful tools in the form of plotting libraries. So for example, for Python, we have matplotlib. And these libraries support plotting functionality on different levels, from very high level ones, like, for example, I might want to change the x-axis from using the linear scale to a log scale, or I might want to do something more low level, maybe change the color for a particular screen pixel, and so on. And these libraries are very useful, but even then, it can still be time-consuming for users, both novices and experts alike, to generate desired plots. So what we're going to do here in the context of plotting is to say we are going to develop a natural language interface for plotting, where our task is going to have the agent perform plotting actions based on natural language requests. So this agent then is going to have access to background knowledge related to the plotting library in question, and that background knowledge comes in the form of documents, for example, API documents, as well as a knowledge-based structure that stores relevant information about that library, that plotting library. So here I have slightly modified my illustration here, where the agent is a specific plotting agent, and the actions that it performs are plotting specific. So one thing I must note here is that, so this is our goal here for the plotting interface, for the natural language interface for plotting. We have not fully yet realized this goal, but we have some exciting initial results that I'm going to be sharing in this talk. So briefly, there's actually prior work on natural language interfaces for plotting. We can actually think of prior natural language interfaces for plotting as falling into two categories. In one category, the user is expected to describe the data. In the other, the user is expected to describe the function that they would like to visualize. So for the first category, basically, where the user describes the data, such an agent can answer questions like, show me medals for hockey and skating by country. So the query is specifying the data that they would like to visualize, which is medals for these particular sports. Or another query that falls in this category is there a seasonal trend for bike usage? In this case, again, we see that the data that we'd like to visualize is specified in the query, which is bike usage data. What happens here is that the system retrieves the relevant data, performs some simple data analysis, and then produces some plot. These types of interfaces are studied quite heavily in human-computer interaction, and they mostly target novice users. In the second category, where the user is expected to describe the function, a good example is a commercial product like Wolfram Alpha, where we can specify the function that we would like to visualize. For example, plot the tangent to x squared at x equals 5. And what the system is doing for us here, it's making use of its knowledge of functions and math to figure out what needs to be plotted. This is quite different from specifying just the data that we would like to visualize. Here we're actually talking about functions, and knowledge of functions is necessary. So to summarize the prior work on natural language interfaces for plotting, so they only allowed, or only required the user to describe the data or the function, and the system is completely in charge of all the plotting details. What that means is that the user doesn't even have to worry about how the plot looks like, what the colors are, and so on. The user just focuses either on the function or the data. So what we're doing here is that we're saying there's actually a third category of plotting natural language interfaces that we can think about, in which the user instructs the system to manipulate a plot directly. So what do I mean by that? So here are some examples of questions from Stack Overflow for Matplotlib. And here is one example question from that forum. How does one change the font size for all elements? Text, labels, title, auto Matplotlib. Here's another question. I have a scatter plot graph. I would like the y-axis to start at max value and go up to 0. The third one, given a signal plot with time index ranging from 0 to 2.6, I want to draw vertical red lines indicating corresponding time index for the list. So what we are seeing here is that these three questions have in common the fact that they are directly talking about manipulating a plot. So the first one, how do I change the font size? The second one, how do I invert the y-axis to start from max value to 0? And the last one, how do I draw vertical lines at specific values? What we found by analyzing quite a lot of questions on Stack Overflow for Matplotlib is that there are many such questions that indicate that actually require direct manipulation of the plot. What we saw is that there's an opportunity to actually automate the process of mapping such natural language query intents, plot intents, to API calls. In particular, what we are going to want to do here is to have an agent that is knowledgeable, so it has access to relevant knowledge, and it's conversational, and so it allows the user to actually fine-tune their plot over multiple turns, and it's going to be stateful, and it's going to remember the entire conversation and the state of the plot along the way. All right, so here, what we're going to do is to treat this problem as a goal-oriented dialogue problem. In particular, we're going to treat it as a slot-based goal-oriented dialogue problem, where we're going to have a bunch of slots that we want to fill given a particular natural language instruction. And the applicable slots are going to be plot type specific. So this is naturally expected because different plot types actually have different knobs that we can tune. So what do I mean by that? So here is one plot type that's supported by our system. So this is a line chart, and we are seeing that a line chart has slots such as an error bar, type of line, marker edge color, marker face color, marker interval, so on. There's also a pie chart, something that we support in our data set, where we are seeing different slots here. For example, we have the radius, the percentage tags, distance from the center, and so on and so on. Here's a 3D surface plot, again, has different slots. Some of the slots are shared across different plots, plot types. So for example, the font size affects the whole plot, or slots that are relevant to axes. So for example, whether or not the y-axis is inverted, and whether or not I'm using a log scale or a linear scale, if the grid lines are present and what kind of grid lines they have, if they're vertical, horizontal, both, and so on. Just to give an idea, we basically support all the plot types in Matplotlib, and here are some of the slots that we deal with in our system, and that's just to give an idea of the scale. And so our learning task, more precisely, is the following. So we have a query. This is the user's plot intent. And the query can be something simple like use the log scale for the x-axis. And we want to map that query to a plotting action. So ultimately, that plotting action in our case is actually just some Python code. But there's an intermediate structure here that has slots and so on, but ultimately we're going to be getting Python code. So when you look at this, you can say, in principle, we can cast this as a problem of program synthesis, where we have natural language and we produce some code. But our setting is actually much simpler than program synthesis. It's much more structured and more focused, so we can actually do something simpler than general purpose methods that we see in program synthesis. So to tackle this task in the way we framed it here, what we would need is to, for a supervised setting, to have data of the form, query, plotting action, and passage. So the query is the user intent. The plotting action is some formal representation, like the slots or the code, and the passage describes what the plotting action is actually doing. But that is actually kind of expensive to obtain. So we're going to split this process up into two steps. So first, we're going to get data of the form query plotting action. And then from there, the goal is to use distance supervision to identify relevant passages that actually describe a plotting action, so that when we get a new query, we can map it to the relevant plotting action based on the description of the passage. So that's the idea here. So we're going to begin by just getting query plotting action pairs. All right, so we're going to get query plotting action pairs, and to facilitate data collection of this form, we make use of structured representations, which we call text plot specifications. So here is an example of a text plot specification, TP spec. It's just a series of values of the form, slot, and value. As I said, the slot types are specific to the plot type. So here we have the T indicating the plot type. And here's a simple example of one text plot specification. So this is for a plot of type line chart. And we have the slots filled out for things like line width, line color, and so on. So the cool thing about having this text representation is that there's a one-to-one mapping between these representations and plots. So this is going to help us when we collect our data. In particular, in the first step, we're going to generate a bunch of these T-specs, and from the T-specs, we get plots. So now we have a lot of plots. And what we're going to want to generate is that given the plots, we want to generate data of the form query plotting action relevant to the plots that we actually have. So we have the plots. Now the second step is going to involve collecting dialogues about the plots that we generated. And for this, we use a very popular method in collecting dialogue data called the Wizard of Oz. In the Wizard of Oz setting, we have two workers. One plays the computer, the other plays the user. So in our setting, the two workers are going to collaborate to replicate a target plot. And only one of the workers actually sees that target plot. And that worker is the user. So the user sees the target plot, describes what it should look like to the other worker. So it might say, the user might say, invert the x-axis, make the font size larger, and so on. So we can think of this scenario as you have this person, they have a plot in mind that they would like to visualize or to generate, but they only describe it in natural language. So in this case, the user doesn't come up with their own plot. We give it to them, and then they just describe it in natural language. So then the second worker, which is the agent, is going to take plotting actions to generate a working plot based on the user instructions. So and the idea is that we have a blank working plot, and we want it to eventually be the same as the target plot. And so when the working plot matches the target plot, then the collaboration, the conversation is over, and we're done. So by doing this, we collected a lot of data points of the form query plotting action. So every time that the user specifies something, gives an instruction to the agent, that is one data point, and the agent takes some plotting action. And for that, we collected over 15,000 data points. This contains over 140,000 tokens, with about 3,000 unique tokens. It's a fairly large data set. It costs about $8,000 to collect it. The average task completion time is about 6 minutes, and we engaged over 400 workers. We set up a separate task to actually figure out the agreement rates across workers, and this was quite high, and it showed that the task is actually fairly easy to do, although it takes a while. Okay, so one thing that we wanted to figure out, having collected this data set, was to say, do we actually have natural language in these instructions? Are the workers actually generating natural language? And we kind of eyeballed the data and it looked fine, but we wanted to get some numbers. So we used a pre-trained language model, GPT-2 in particular, to evaluate the naturalness of the utterances. And so here's the distribution of complexity over the utterances of the data set. And so we get quite a huge range of different complexity levels for different utterances. But the average is quite high, and we wanted to figure out why the complexity is very high here. And we looked at a few examples of the utterances in the data set. So here's one, for example. It says, add a blank outline to the chart. And what is happening here is that when we reach the word outline, the complexity goes up quite high because the context in which we find the word outline is actually quite different from the context that you would find in generic internet texts on which GPT-2 is trained. Here's another example. Increase the cap size of the error bar, but don't touch the thickness. So again, when we come across cap size in this context, it's completely unexpected. So we see that complexity goes up around there, and this results in a sentence with high complexity. So the sentences are actually fairly natural in the text, in the data set. There were some sentences that kind of mix natural language with a little bit of code or slot filling type language, but for the most part, these were very natural utterances. So having established that the data is actually reasonably good, we trained various models on the data set, and we found that the best performing model is the sequence-to-sequence model. And the sequence-to-sequence model that we have one here is one where the memory bank has access to the hidden states of the input request, but also has access to relevant knowledge of the relevant to the plotting library that we're working with. So this is essentially what it looks like. So this is the goal model. So we wanted to take as input some image and the input utterance and produce an updated plot. So here you can see that there's a database structure, some relevant knowledge that is stored, and we want that information to be part of the attention memory bank. So right now, everything else is pretty much part of the model. The knowledge aspect is not yet there, but we have an interesting model where we got interesting results, and we're currently working on incorporating the knowledge aspect here. So what I'm going to do now is to show a 1-minute clip of that model working, and it's just going to show an interactive tool that allows us to interactively plot in natural language. And what we are going to see is that the user can actually use paraphrases. So for the same kind of operation, we don't have to use just one phrase. So this is not hard-coded, so it's not limited to the phrases in the training set. We're also going to see that we can load some pre-trained specified pre-specified dialogues. This is actually data from our dialogues from our data set. And for both the paraphrases and the pre-specified dialogues, this is synthetic data. So the data is going to be generated by the system. But we can actually also allow you to load your own custom data set, and that will also be in the clip. And for this, we'll be showing for COVID-19 US confirmed cases. And I'm just going to start it. So here's the clip. You can just look at the texts that appears in the notebook. The captions are not super useful. All right, so that's the clip, and that's the current system that we have and how it works. Here are some numbers, and the best performing model that you just saw performs reasonably well on most natural language requests, but on the data sets, performance is still in the 60s in terms of exact match performance on the data set. So there's still some gap before we can actually do well on this data set. In particular, we did human experiments to see how well a human would perform on this data set. So taking the instructions that are given by the workers and trying to generate the plots that they want. And the human was able to get about 80% performance. So there's still quite a wide gap between the current model and human performance. So this is where we are aiming to have our relevant knowledge component come in and hopefully close the gap. So our code and dataset is available at this GitHub repository, so you can check it out. And that's it. So thanks for your time.
Thank you very much for the really cool talk. We do have several questions, and we have about 5 minutes for a quick discussion. So I will read out the questions that we see here. The first one is, how difficult do you think it would be to adapt your method to a different plotting library, keeping the same inputs in natural language?
Right, yeah, so that's a very good question. So with all these plotting libraries, so this is targeted for the Python, the matplotlib library. Suppose that you want to switch to, say, ggnuplot or maybe Mathematica. For the plots, so the plot types, they really have sort of similar knobs that we can tune. Like for the line chart, we have the same slots pretty much regardless of what the underlying library is. So the mapping, or the thing that changes is really the mapping between the slots and the underlying programming language or the underlying language. So so that's one thing that we actually want to be able to do with the goal of using relevant background knowledge, so we can actually use additional libraries instead of just one single library without having to get more workers to label data. But that's a good question.
Mm-hmm. Thanks. The next two questions are sort of related. So the first one is, in the beginning, you mentioned using NLP to automate mundane data science tasks. What other mundane tasks do you envision being automated in the future? So that's the first question. And the related question is, I think, are you considering using a similar approach for things other than plots? For example, writing simple pieces of code?
Right. Yeah. So both are great questions. So in terms of the mundane tasks, so we have a concurrent project that I'm collaborating with my colleague from databases, where we want to automate SQL query generation. So basically, SQL is very good. It's a very good language for retrieving useful data from structured sources, but some people don't necessarily know SQL. So what we're doing is taking natural language to SQL, and that project is underway. What is different from other work that looks at natural language to SQL is that we are directly working with speech to SQL. So we want the person actually to speak the SQL and then generate, automate the actual SQL structure representation. So the second question, which is about how we can, what was the second question, sorry? Just the last part, I think.
Yeah, the second question was, are you considering using a similar approach for things other than plots, like simple pieces of code?
Oh yeah, simple pieces of code. Yeah, so this is, so that's a very interesting question. So that would fall under program synthesis again. So here, this is exactly what we're doing, which is taking natural language to simple pieces of code. So I'd say, I mean, SQL is, we can think of it as a simple piece of code as well. But in general, we are doing sort of a specialized version of code generation, but we're not generating very long structured programs like what you'd find in, you know, full-blown, full-fledged program synthesis. But indeed, right now we are only looking at SQL.
Mm-hmm. Great. We have a few more questions here. So the next one is, what are your thoughts on handling ambiguous plot specifications? Do you think there is a place for the plot drawer to ask clarification questions to the requester?
Right, yeah, so that's a great question. So we gave that option to the plotting agent to basically ask clarification questions, because indeed that's why the human performance is not 100% yet. Part of it is because of ambiguity. And we gave that option in the data generation process. Unfortunately, what ended up happening was that we didn't have a lot of cases where there were clarification questions, so we couldn't really use them to train the model. But I think that is definitely something that needs to be studied more, and I think that's an excellent question, yes.
Great. So one more question, I think. So this is actually from me. So I don't know the plot language in detail, but what happens when someone asks to modify a part of the program that was executed before? Can you go back to, can you update parts of the program, or say in an interactive scenario, some n steps happened and then the n+1th step attempts to modify something that has already been executed? How does that work?
Yeah, well, yeah, so that's a great question. So everything is stateful. So you can indeed refer to previous steps. So right now it mostly works for we have for sure tested it on if the instruction is just one time step before, like if I say make the font larger, I can then next time just say larger, and then it knows that what I'm referring to, the font size. So yeah, so right now we have a simple way of maintaining state, but the idea is indeed that state needs to be modeled, and that's the whole point of having this be conversational, because you can't necessarily specify everything in one go, and you want to be able to have the user not lose their work and build on it incrementally. Yeah.
Great. Thanks a lot for answering these questions. We really enjoyed it. And you will be there at the hallway chats at the end of the day, right?
Yes, I'll be there as well if people want to.
Yes, great.
Yes.
Thank you very much. Thanks again for the presentation. And I will hand it over to Matt now. Thanks.
Sure.
All right. Emma, if you could get your presentation started. Let's see, I'm going to unmute you. And spotlight your video. Okay. So I am pleased to introduce Emma Strubell, who soon will be starting at the Language Technologies Institute at Carnegie Mellon University as an assistant professor. She's currently visiting Facebook AI Research in Seattle. Prior to that, she finished a PhD with Andrew McCallum at UMass Amherst, and she has done a lot of really interesting work, including winning a Best Paper Award at EMLP in 2018. And today she's going to talk to us about learning to live with BERT. Emma, you can take it away.
Great, and y'all can see my slides and everything?
Yes, it looks great.
Okay, thanks. Yes, thanks for the wonderful introduction. Yeah, so basically, actually, let me just adjust this a little bit. Okay. Yeah, so I'm doing a year postdoc at FAIR before starting at CMU in the fall. And what I've been telling people is my goal this year at FAIR has been to figure out, how to be able to use, train and use pre-trained language models like BERT, once I'm at CMU in the fall, and like the computational resources that I have available are vastly reduced. So today I want to talk to you a bit about why that's important to me, even as an academic. And I'm going to survey some recent approaches for making these models more efficient, and then briefly conclude by identifying some exciting future directions. Oops. Okay, so as you've probably already noticed, recent advances in techniques and improvements in hardware for training deep neural networks have enabled really impressive accuracy improvements across many fundamental tasks in machine learning. And in NLP, of course, we name these models after Muppets, and more recently, like other cartoon characters from The Simpsons, with the largest and most computationally hungry models obtaining the highest scores. So here I've plotted on a log scale the number of GPU hours required to train 4 recent NLP approaches, so the transformer, Elmo and BERT, and the evolved transformer, which uses neural architecture search applied to the transformer for machine translation. And so the number of GPU hours required to train these models has increased like super exponentially over the past 3 years. And of course, since I originally wrote the paper where we quantified these things, this trend has definitely continued. So Google's Mina chatbot, which was announced in January, was trained using neural architecture search on 2,048 TPU cores for an entire month. And of course, GPT-3 was just announced about a month ago. And it's, for reasons of like reporting and hardware and stuff, it's hard to place it exactly on this graph, although like I guarantee you it's kind of like up where that arrow is pointing. But it is estimated that it costs about $12 million US in worth of cloud compute to train a single model. Just as a point of comparison from our paper, we estimated that training the evolved transformer required only like about $150,000 in cloud resources. So the point I want to make here is that the energy consumption of these models is growing in step with their computational requirements. So here I've listed the carbon footprint in pounds of a number of common benchmarks. Well, I guess it used to be common, such as round trip air travel for one passenger between New York City and San Francisco, or the carbon emissions of the average American for 1 year. So this is all from the paper I presented at ACL last year, where we quantified the energy required to train and develop deep neural network models for NLP, and then converted that to estimated costs in terms of cloud compute credits and carbon footprint. And so we find, for example, that the GPU time required for me to tune and develop the model that I got that Best Paper Award from at UMNLP a couple years ago, like effectively doubled my carbon emissions that I would have otherwise produced that year. And training a machine translation model using neural architecture search, if done using GPUs, so typically it's done using TPUs, can produce more than twice as much carbon as a car during its lifetime, including fuel. And as I pointed out earlier, we also estimated this model will cost about $150,000 in TPUs to train, which highlights another really important side effect of the enormous computational requirements of these models, which is that they're becoming increasingly limited to a really small set of researchers and practitioners who have access to the enormous computational resources that are required to develop and deploy them. Most of the carbon footprints that we computed for that paper and that I'm citing here today in this plot are for training really large models, like large pre-trained language models like BERT, or I think you heard earlier about BART, et cetera. And you may be thinking, let's save the training of those models for the big companies and like whoever else really cares about like supervised English leaderboard chasing. But I actually think that it would be hugely beneficial for a lot like researchers and practitioners outside of these few privileged institutions who are just interested in sort of making these common benchmark numbers go higher. They're also interested in other things, but yeah, I think it'd be really beneficial for researchers and practitioners outside these privileged places to be able to work with these models. So originally, I think I was going to frame this as like, why should you care about making pre-trained language models more efficient? But instead, I'm going to describe why I care and then let you decide, because a lot of the problems that I care about could really benefit from making these models more efficient. But there's also a lot of interesting problems that like, maybe shouldn't involve pre-training language models, and that's fine too. I'm guessing like many of you, I'm mainly interested in solving problems where solutions can be found in text. So for example, here I'm showing a caricature of a project I worked on with some real life material scientists at MIT, where our goal was to automatically extract inorganic materials recipes from the text of journal articles. And so as I'm sure you know, the reality of getting out this like recipe requires inducing some kind of structured annotation over the structured text. In our case, this is some form of syntax and semantics. You can also think of this as like as a triple or tuple in a knowledge base. So this is an example of a problem that I think is really interesting. And some of the best approaches for obtaining the structured information that we want from the raw text require good distributed representations of words. And large language model pre-training does a really great job of building representations of words in context. And in a way where you can get pretty substantial improvements, not only in the supervised learning setting, which is typically how these models are evaluated. Although I guess actually the GPT-3 paper did look at few-shot learning specifically, but also in the unsupervised setting, in out-of-domain performance, where your data comes from a distribution that differs from the data that you trained on. Especially, or as long as you have a large corpus of unlabeled text in the domain that you care about, which I actually think is like fairly common, or at least not incredibly difficult to obtain. So my point here is that even though I'm not necessarily trying to like beat Google on a question answering leaderboard, as someone who's interested in making NLP tools that are useful for extracting structured information from unstructured text across a wide variety of domains, for example, our collaborators in material science, it'd still be really useful for me to be able to train and use the representations that come out of these big pre-trained language models. Because even fine-tuning can be super inefficient because you still have to fine-tune all the parameters of these models typically. Oh, yeah, okay. Okay, so I started by pointing out that although these models can provide high-quality representations of word and context that can be useful for researchers such as myself, this comes at a huge computational cost that's inaccessible to most researchers and practitioners. So now I want to talk about some recent techniques for scaling down these models, ideally having minimal impact on the quality of the representations that they produce. But first, I'm going to like really briefly summarize how they work, just to make sure we're all on the same page before describing how they might be made more efficient. Although I think I'm going to go through this quickly because if you've been at previous talks, like I'm sure this has been covered. Yes, okay. So, so essentially all these language models are based on the transformer architecture. This consists of a bunch of stacked neural network layers with the output of each layer provided as input to the next. So this allows the model to build up these increasingly complex representations of the text with each additional layer. And there's actually some empirical evidence that the representations in the lower layers are specializing to lower level linguistic information like part of speech, whereas higher layers are modeling higher level information. So if you want a survey on that, which is super interesting, you can check out the BERTology paper by Anna Roberts. I want to plug that. And then as a quick reminder, this is like what the internal mechanism looks like inside each of those layers. So this is the figure from the original transformer paper. Each layer consists of multi-head self-attention, which requires runtime that's quadratic in the length of the input. That's an important fact. Followed by a large feed-forward projection. So typically this is a projection that's like projecting up into like an embedding space that's 4 times the size of the original representation in between each layer. And then there's a softmax layer on the top of the whole network after the final layer that's predicting into the full vocabulary of tokens. Okay, so this basic architecture is the basis for lots of state-of-the-art NLP models right now, including BERT-style mass language models. And so there's a number of architectures that do differ slightly. And so for example, BART is like an encoder-decoder, but it's still based on the transformer architecture. So the overall structure, I think, is similar enough that many of the same ideas apply. Okay, and of course, the way that mass language modeling works is that, rather than providing all the tokens to the model, each time a sentence is observed during training, some of its tokens are masked. And the objective is that the model is trained to perform, that the model is trained to predict what the masked tokens are. And so in practice, it's been found it's best to mask about 15% of the tokens. So in this fragment, that would be 1 token. And we don't actually train on sentences anymore. We train on these long sequences of sentences of about 128 to 512 tokens in length. And of course, the tokens that we're using are actually byte pair encoded subword units, typically with a vocabulary size of about 30,000 word pieces. So this alternative training objective, as an alternative to sort of sequential or left to right in languages that, or I guess reading direction encoding, where each token is predicted incrementally from the past context, allows for much faster training because you can predict all the masked words, in parallel on GPUs, and that's in part what's facilitated like the training of these enormous models on lots of data, and then thus better performance. Okay, so how can we improve the efficiency of training these models? So Roy Schwartz and others at AI2 characterize this in a simple equation in their Green AI paper, which I'm just going to use because I think it's really nice. So the cost of obtaining a result is a function or is directly proportional to the cost of processing a single example with a given model, multiplied by the size of the data set, the number of examples, and multiplied by the number of hyperparameter configurations required to fit a good model. So I'm going to start by describing some recent techniques for reducing the computation required to process one example, which is by far the most popular approach to improving efficiency in these models. So if you don't want to work in a crowded space, like don't start working on that. Okay, so the premise behind a lot of these techniques is that these large models are actually really over-parameterized, but training a smaller model from scratch just doesn't perform as well as training a larger model first and then making it smaller. So there's actually been a lot of different recent empirical work suggesting that if you have a fixed computation budget, you want to basically have a large model and train it for a shorter period of time, and then potentially like prune it down or distill it. So we think this is like an optimization issue, and there's this interesting recent line of work that's like somewhat controversial based on the lottery ticket hypothesis, which suggests that larger models work better because their random parameter initializations are more likely to contain lucky values that converge to good performance. So one really popular approach to making models smaller is known as knowledge distillation. This is kind of like an older idea, but the idea is to take a large model that, like a really large model that works well, and then distill it into a smaller model by training the smaller model to imitate the larger model's predictions and activations. So the picture here is from a recent paper that I think, as far as I know, or maybe as of a couple months ago, there's sort of the best distillation model. So it's showing 2 of these like transformer self-attention layers, and the dotted lines are showing the places where the model is trained to produce the same representations as the larger model. So you basically enforce during training that those intermediate representations are the same as the larger model. And this works reasonably well. As far as I know, as I said, there still aren't any approaches for distilling BERT that work as well as the original model. And of course, this also requires that you already have like a big pre-trained model sitting around and you just want to make it smaller. It doesn't really help you with the actual task of training. So another popular approach is taking a pre-trained model and removing or pruning unnecessary model parameters. So there's a lot of different examples of this. So you can prune different parts of the model or propose different metrics for what makes a parameter prunable. The most common example is just to prune the smallest weights. And this figure is from an interesting paper from EMLP 2018, where they did some nice analysis of what the multiple self-attention heads in, I believe, a model trained to do machine translation were actually doing. Yeah, I mean, so they were pruning like self-attention heads. And you can see here that some looked like they specialized in subject-verb or verb-object attention, as well as maybe more boring things like attending to various punctuation or the previous or next token. So another approach that I like that is similar to pruning is quantization. So here, instead of removing parameters, the goal is to decrease their precision. So you want to decrease the number of possible values that each parameter can take on, or like the expressivity of each parameter. So typically models are trained using 32 or 16-bit floating point numbers, but actually this can be reduced as low as 2 to 4 bits per parameter. So each parameter only has 4 to 8 different values. So this can like vastly reduce memory requirements. And if you have the right hardware, this can also be extremely fast. I guess the problem is that you have to have specialized hardware that can actually do math in these lower precision values. And so this is especially promising for like embedded systems and like on-device compute. But as with training models with fewer parameters, training models with less expressive parameters is a lot more challenging than taking a pre-trained model and quantizing it post hoc. So again, you generally need to start with a big model and then make it smaller in order to get the best performance. Okay, so there's this last sort of like bucket of approaches that I'm going to refer to as bespoke architectures. And I think I have to give Jonathan Bisk credit for this this terminology, but I really like it. So these are sort of like model-specific modifications to the transformer architecture, usually to reduce like the n-squared computation all pairs self-attention. That's basically the computation bottleneck of the transformer. So I guess as like a side note, going back to our little illustration of the transformer, just in my personal experience, profiling like a Roberta base language model, about half of inference time is spent in the self-attention part of the model, and then about a quarter of it is spent in the feed-forward layers and a quarter in the softmax. So yeah, so since the bulk of the computation is happening in the self-attention, most approaches focus on reducing the computation there. And it makes intuitive sense that we should be able to do this since every token should really not have to attend to every other token at every single layer in the network. In particular, since the model is sort of like iteratively aggregating information from the context into each token's representation at each layer. So one recently popular example of this is the reformer, which is using hashing to cluster token representations like in the attention that are being provided to the attention. And then the self-attention is only computed between tokens within the same cluster. So these are tokens with the most similar representations that are going to have the highest dot product anyway. And another is factorized attention or sparse attention. So here the model is attending to a subset of its neighbors according to a fixed width pattern. And then you can combine that sort of like other fixed width patterns along other dimensions so that every token gets looked at, but like not quite as much. So this is like looking at every other token or every 3. And then another interesting approach is like training the model to attend to fewer tokens by learning, typically for like a given token, to attend to a smaller or larger window of context. That's sort of like context specific. So one of the nice things about this set of approaches is that unlike the other methods, they can be used to train the model more quickly from scratch. But of course, there's always a trade-off between efficiency and accuracy. and like sort of like which hardware you're actually using. So I kind of think like these adaptive context size models are like really going to give you more gains like on CPUs rather than GPUs, just because like they're not actually, you know, designed for these huge batch computations. Yeah, so another thing that I think, I guess overall, all these approaches I just described that kind of remains untested is like how well they actually generalize to new data. So I mean, I have concern, I mean, I think there was a paper about this, but a recent paper about this. You know, I have concerns about once you're like removing all these parameters, like, and then, you know, evaluating on some specific data, like how well these models are actually going to generalize compared to sort of like the vanilla language models to, you know, data from new domains, you know, without additional fine tuning. Or also how efficiently they can be fine-tuned. So to take a recent example, Albert was proposed. Albert is like another, you know, more efficient version of BERT that was proposed at this past iClear, or smaller and more efficient BERT. Then in a later analysis on a fine-tuning benchmark called Hulk, it was found that Albert actually took a lot more computation than like a baseline BERT to fine-tune because of the way it was using parameter sharing, made learning sort of like harder, like optimization harder. So it took like more, they had to look at more examples in order to converge to the same result. Yeah, so sorry, okay, now I'm going, I think it'd be great to have better standardized benchmarks for this, but that is a topic for another talk. Okay. All right, so that was just a sampling of the many approaches that have recently emerged for improving the per example processing time during training or inference. And in this talk, I'm not going to go into detail about approaches for improving the number of hyperparameter configurations, except to say that model sensitivity to hyperparameters is woefully underreported in papers. And I think we need to do a lot better to characterize when models are more or less sensitive to hyperparameters. So there's also already another paper that's about this, and we should listen to them. Yeah, because I mean, models that are more sensitive to hyperparameters are going to take effectively like a lot more compute to actually fine tune and deploy on new data. But so what I've been more interested in looking at recently is reducing the amount of data that these models are trained on, because I think there's actually a lot of potential leeway there, and potentially some interesting things to learn from better understanding, you know, which examples are informative for training these models and like what are these models actually learning. So this is like, the idea of reducing dataset size is actually like starkly in contrast with the recent trend. So this is an example tweet from one of the developers of T5, you know, where he says, hot take, the most surprising thing about BERT isn't how well it worked when it was proposed, but how much better it would have worked if they had just pre-trained for longer on a more diverse data set. And so to see what he's talking about, so he developed this T5 model. So since BERT was first released, these big companies have been clamoring to scale up training in terms of both model size and amount of training data, and these things go hand in hand. And scaling does continue to improve performance, you know, even from GPT-3 earlier this month on these supervised English benchmarks that people evaluate on in particular. But so what I want to show here with all these numbers is that, to me at least, it seems like naively adding more data is just not an efficient way to improve performance. So we see similar trends across Roberta and XLNet, which are two post-BERT language models from Facebook and Google, respectively, where with about 10 times more data, the same model can obtain about a point or two absolute in terms of F1 or accuracy on some of these common benchmarks, which is equivalent to about a 10 to 20% error reduction. And yeah, so there's actually a nice recent paper from OpenAI showing, you know, empirically that language model test loss appears to have like a power law relationship with data set size. So you can just compute that coefficient. But my intuition is that we really don't need all 126 gigabytes or like 30 billion tokens of training data to learn models that perform just as well. I suspect there's a substantial amount of redundancy in that data. So as an alternative to making models smaller, I think it'd be really beneficial if we could figure out how to better select an informative subset of examples from these enormous corpora for training the model. Oh, yes. And so as a very relevant side note, the source of the data definitely matters. So there's some experiments from the large set of experiments that were published as part of the T5 paper. And they found that training on a smaller amount of in-domain data, so for example, training on Wikipedia when the test data was based on Wikipedia, or similarly for fiction books, outperforms training on a larger amount of in-domain data from, for example, a web crawl. And this was also found to be the case in a number of other papers. So the BERT paper showed that training on in-domain text from scientific papers led to much better performance than out-of-the-box BERT, which is trained on Wikipedia and books. And there's another more recent work from the same group at AI2 that also showed that a second, post pre-training step, fine-tuning on in-domain data also helps downstream performance when you have a data distribution shift. So this is just some more evidence that being able to like pre-train or at least like post pre-train your own models it would be really helpful. And we also have experienced this with our work in the material science domain, where we definitely got improvements from like training an Elmo on a large corpus of material science text. Okay, so this seems like a promising direction. So what work has actually been done towards this end of sort of like improving sample efficiency of these models? So the most relevant thing that I know of, and I would love for people to send me other papers that are doing this, is the Electra model from Kevin Clark and collaborators at Stanford and Google. And I think that, I'm personally, at least in my world, I think this is like somewhat overlooked in favor of like Albert at AgClear this year, but I think this is like a much more exciting model. So they proposed an alternative to the typical mass language modeling objective that I described before. So instead of doing mass language modeling, they set up training such that the model gets a signal from every token in every example. So I think this is really important. So rather than only 15%, yeah, they get a signal from every token. They do this by dividing the model into a generator and a discriminator. So the generator is basically just a small BERT, like a small typical mass language model. And then its predictions are provided to the discriminator. And the discriminator's objective is to just perform a binary classification on each token to identify whether each token was like the original token or was produced by the generator. So something that I think is interesting is that, and so basically they're able to train the model, in less time with the same amount of parameters, sort of using this more sample efficient setup, which is what's exciting to me. And another thing that is interesting is they found that this model performed best when the two models were trained together at the same time. So I think this is interesting because essentially in this setting, the generator is inducing like a natural curriculum for the discriminator, since presumably early during training, the generator is, generating poor predictions. And so it's like the discriminator's task is easier. And this raises an interesting idea. Maybe we should be doing curriculum learning or active learning for language model pre-training. And there was a form of this actually in the original BERT paper, where they actually trained on shorter sequences first and then like switched over to longer sequences later during training. Although I think this is not typical to do anymore because subsequent papers found it didn't really like improve final convergence accuracy, although I'd imagine it would improve wall clock training time. This is something that I've been taking a look at. So far, I haven't gotten anything super straightforward to work. And one key question that arises is, if you want to design a curriculum, you need to have some metric for like what makes an example easy or difficult. What does make an example easy versus difficult for a large language model?
I'm sorry to interrupt here. This is a 2-minute warning.
Oh, really?
Yep.
Okay. Really? Oh man. But okay. Okay, so basically to get a sense for this, I applied a simple study originally proposed for computer vision to better understand which examples are more or less difficult for mass language models. So it's super straightforward. Basically just counting during training, like for which examples is the model sort of like shifting its predictions most frequently. So the most forgettable examples are going to be the most difficult examples, and least forgettable are going to be the easiest. So I did this on like a per token basis. And this is an example of what those counts like actually looked like. So I'm just going to due to time, I'm just going to skip to the next slide. So this is like aggregating those counts over the entire corpus. And so basically the takeaway is that, I guess it's kind of what you would expect. So like determiners and punctuation and things are sort of like the least forgettable or easiest tokens. The model is just like not forgetting at all. And then the most forgettable tokens, or the hardest ones, are these like really specific verbs and nouns. So I think this makes sense because these are like the words that you would expect to see like sort of the highest entropy distributions for, like these more difficult or most forgettable words are the ones you would expect to see the highest entropy distribution for. But also, like, if we were to use this as a metric for curriculum, like it's not clear this is the metric that you would want, because it's like, I think a lot of these examples are just really ambiguous. So, who's to say whether the next word is shimmer or sparkle, or like which of those is sort of like correct given the context. So this is basically just a plot of like those sort of same numbers, but also like looking at token frequency. Sorry, I timed this, but I think I like rambled more than I meant to. So yeah, so I guess my takeaway here is that determining example difficulty in a way that's really going to impact training is a bit harder than just looking at simple metrics like token or background frequency, or even like output distribution entropy. Since focusing on helplessly ambiguous examples, like sparkle versus shimmer, maybe, like isn't going to accelerate training either. In addition to maybe like just looking at the most frequent examples, which if I had described this plot would maybe make more sense. So we need some middle ground way of finding examples that'll help the model learn to disambiguate predictions that are actually disambiguatable. Okay, so I summarized a bunch of work that's out there. I took too long, and I gave you a little taste of some of the stuff I've been thinking about lately. So now I'm about done. I was gonna quickly conclude by summarizing a few future directions that I'm excited about, but I think I'm probably like already over time. So I'll just show you the slide and I will take questions.
Okay, go ahead and like spend a minute on this. It's fine.
Okay. Okay, so one thing I'd like to better understand is like the extent to which we can separate generic linguistic knowledge in pre-trained language models. It's like these implicit models of syntax and coreference that there's evidence that they're learning from domain-specific representations of sort of specific entities and events that are tied to the exact data that they're trained on. And then of course, like better understanding this would hopefully lead to how can we design models that can separate these concerns to the extent possible in order to adapt better and faster to new data distributions. And then another important direction that I think a lot of people are interested in, and that has been discussed, I think, at this conference, is how can we better align pre-training objectives and architectures with the actual downstream tasks and meaning that we care about. So for example, if we want to use language models as KBs, or even just do human-like dialogue, we need them to be able to predictably produce facts and not hallucinations. So this table from a recent paper highlights an example of this in a vanilla BERT, which produces essentially the same predictions to fill in a robin is a versus a robin is not a, which seems like something that's almost like universally, not a property that we want these models to have. And then a third direction I'm excited about is exploring the interactions across different modalities. So for example, language and vision. So I think this is not only vital for building models that are capable of reasoning about a huge class of sort of like common sense or just like general knowledge that is not written down in the text that we have available. But there's also an area where models are currently like extremely inefficient. We're essentially right now just like gluing together these already enormous models from NLP and computer vision. But at the same time, I think there's like so many opportunities to actually leverage information across modalities in order to reduce the amount of computation necessary in sort of like each individual modality. Yeah, so that was my ramble. I hope you enjoyed it. Thank you so much for listening, and I am happy to take questions.
Great, thank you, nice talk. I'm going to go through the questions that we have here. First question is from Han Guo, who says, is it possible to construct some kind of cost per performance for each model component so that a practitioner can optimally decide based on their needs?
Yeah, so this is really hard. So the reason this is hard is or the reason that I think this is hard. So I think we need better benchmarks for this. And I think we need like a centralized benchmark for this where people are like uploading models and they're being evaluated on comparable hardware and potentially across different hardwares like CPUs versus GPUs. So like the commonly reported metrics for efficiency are basically like wall clock time, like wall clock training time, or maybe inference time, or floating point operations. And so I think both of these are, don't really capture the full picture. So floating point operations basically completely disregards like the exact hardware that you're running on. So for example, when you make models more sparse, typically on GPUs, you're not actually, like the model is just computing the result for a bunch of zeros and not necessarily doing like actual sparse computations. So like a sparse model may actually have no like wall clock speed up on a GPU versus a non-sparse model. And then wall clock time also doesn't tell the whole picture because as I learned very viscerally when we were trying to basically like estimate like these energy costs across different models based on sort of them reporting wall clock time and hardware, it's like actually very, you have to make so many assumptions. So like, yeah, you're doing a lot of different assumptions. It's really hard to compare wall clock time across different hardware. And like much harder if it'd be nice to be able to answer the question like, okay, this thing was trained on GPU or this thing was trained on TPU, like how realistic would it be for me to train it on like a different piece of hardware or something like this? And you just like really can't answer that question, at least without, I think, maybe I need to talk to some systems people more, but I think it's hard. So there's like memory locality issues and all these things of like specific implementations. So now I've forgotten what the original question was, but I think that such a metric does not exist. I think directly measuring like the energy draw of an approach is like kind of the best way to actually do that, like on a specific piece of hardware, but we don't have that yet. Like, yeah.
Next question is from Anonymous and says, you've talked a lot about how to make computation and training of transformers more efficient. Is that the answer for how to make progress from academia?
Yeah, so I tried to address this a little bit in the beginning of my talk, where I think for me, so yeah, but so, okay, I think the ways of making transformers and stuff more efficient, like, so I think exactly what I'm trying to argue is that just like throwing more data at it and making the models bigger is not the way to move forward. Like I mean, at least in my research, like it really seems like having good representations of words in context that are like these embedded representations are really useful for a lot of very practical tasks. I don't think that we need to have these enormous models in order to get representations that are just as good, or like these models that are enormous and like trained for a really long time. Yeah, so like unfortunately right now, I think it's hard for academic researchers to even approach this because you have to kind of start from the models where they are, which is very large. But I do think that some people need to think about this, and yeah.
Yeah, great. I think we have time for one more short question. What's your take on the argument, for example, from the GPT-3 paper? While pre-training is expensive, fine-tuning costs of these models is low and accessible.
I mean, I guess it's low compared to pre-training, but like, I mean, my own personal experience is I was trying to, fine-tune a language model to do co-reference, but I couldn't without using like a GPU that had 32 gigabytes of RAM unless I like vastly, actually, no, I think that was like batch size 1. So I disagree with that. I think maybe that's the perspective of someone who's not actually like limited in resources. I did read that in the GPT paper, and I was kind of like, okay.
Yeah, great. Thank you. This was a wonderful talk.
Thanks for having me.
I think now I will hand it over to Samir, who is going to play the contributed, play videos for contributed talks.
All right, thanks, Matt, and thanks, Emma, for the talk. I will steal the screen from you. All right, and we will be playing all the videos now before the poster session. And they're in random order.
Hi everyone, my name is Yuchen Lin, and we are presenting a new test generation challenge for generative common sense reasoning. It's a joint work by USC, SI, UW, and AI2. What motivates our research is that the most current common sense reasoning datasets mainly focus on discriminative reasoning, such as common sense QA, the SWAG dataset. However, humans not only use their common sense for understanding tests, but also for generating sentences. We thus propose a new dataset named CommonGen. As we can see, an input to CommonGen is a concept set, which is a collection of the objects and action words. For example, a dog, a frisbee, the action catch, the action throw. The desired output is a sentence that describes an everyday scenario in our daily life using as many given concepts as possible. A simple example like the second one, a dog catches the frisbee when the boy throws it. Why is this problem hard? First of all, it needs much relational common sense knowledge about given concepts, and they are latent and compositional. For example, we can see this particular real example in our dataset. We need to know a list of facts which are latent and find the best composition of them for writing the final sentence. A woman in a gym exercise by weaving ropes tied to a wall. We analyzed our dataset and found that it covers different types of knowledge, such as spatial knowledge, human behaviors, the object properties, and other general ones. Second, the dataset needs compositional generalization ability so that it can work for unseen combinations of concepts. For example, in the training time, we can see such examples about apple bag put, apple tree pick, apple basket wash. While in the testing time, the model needs to deal with a more challenging example like this one, pear, basket, pick, put, and tree. The model has never seen the concept pair in the training time or the combinations of any two of the given concepts. While we still hope the machines can generate a sentence like a girl picks some pear from a tree and put them into a basket. So this is also some statistics of our dataset, and note that all the concept pairs in the testing examples are not shown in the training before. We have tested a comprehensive list of models on our dataset. These are some experimental results with several automatic evaluation metrics. We also did manual evaluation by asking humans to compare and rank the model generations. In the end, we found that T5 large, after fine-tuning, performed the best, but it's still far from human performance. This is a case study for qualitative analysis of the model generations. We can see that there is still a gap between humans and model generations. For example, the sentences written by humans are more natural and commonsensical in our daily life. However, if you look at GPT-2, it's like hands washing soap on the sink. Or BERT, a woman washes her hand with a sink of soaps. So these are less natural or plausible in our daily life. We also did some transfer learning analysis. We used CommonGen models to generate some choice-specific context sentences for the downstream applications, such as common sense QA. And we found that the best models like T5, BERT, and UniLM, they can be very helpful for generating additional evidence for downstream applications that needs common sense reasoning. Thank you very much for listening. There are some links to the paper and the portal page, and you can email me for more questions.
Hello everyone. Today I'll talk about my work on contrastive entity linkage. This is joint work with Bunyamin, Hao, Luna, Christos, and Lisa. Consider the two entities in this image. Are they the same or are they different? Well, it's unclear. While they are essentially the same product, they have the same manufacturer, brand, and model, they also have an important difference, storage size. The iPhone on the left has 64 GB and the one on the right has 256 GB. Whether these entities are the same or not may even be context dependent. We refer to these entities as entity variations. Entity variations share the same values across a set of core attributes called base attributes, but differ from each other along a few crucial attributes, such as storage size in this example, which we refer to as variational attributes. Entity linkage in domains such as products need to identify variations along with duplicates and distinct products. Our contribution in this work are threefold. First, we propose a scalable, unsupervised approach, VARSPOT, to discover variational attributes present in unstructured text. Second, we extend the traditional task of two-class entity linkage to three-class setting, where along with distinct and duplicate pairs, we also need to identify entity variations. We propose a novel framework, contrastive entity linkage, for this task. Finally, we perform empirical evaluation in 3 different domains to show the generality of our approach, and we use 3 different state-of-the-art entity linkage frameworks. Here is a table that positions our work among the existing literature. Existing entity linkage approaches only identify duplicates. Approaches such as group identify variations or near identical entities, but assume variational attributes are present as structured fields. Finally, there are approaches that extract product attributes from unstructured text for a small predefined set of attributes and are supervised in our nature. Our proposed approach, on the other hand, can not only identify both duplicates and variations, but also extracts variational attributes in unstructured text to help identify these pairs. The main challenge for entity linkage systems is in the identification of variational attributes in unstructured text. There are several variational attributes, and they differ for different product categories. To overcome this, we propose a VARSPOT algorithm that extracts variational attributes from unstructured text in an unsupervised manner. It has 2 phases. In the first phase, it identifies potential entity variations by linking an entities in a catalog to itself. This is motivated by 2 properties. First, catalogs typically contain very few duplicates, and most of the variations are typically very similar to each other. Having identified the potential variations in a single catalog, next we extract the VARSPOT. Next, the VARSPOT algorithm extracts contrast features that correspond to variational attributes. Here, the tokens 64 GB and 256 GB are extracted as contrast features as they correspond to variational attribute storage size. Having extracted our contrast features, we now describe our contrastive entity linkage framework. First, we extract the contrast features from each of these catalogs and combine them. Then, for each entity in the catalog, we extract phrases corresponding to contrast features and add them as a separate record attribute. We then train a multi-class classifier using the label data to classify a pair of records as either duplicates, variations, or distinct. To evaluate the effectiveness of our approach, we performed empirical evaluation on data sets of varying sizes from 3 different domains: software, music, and groceries. Further, we considered 3 state-of-the-art entity linkage frameworks. First, we show some qualitative results. As described earlier, the first step of VARSPOT algorithm identifies potential variations by linking entities in a catalog to itself. Here are some pairs discovered by our algorithm. We first see that while editions differ for software and packet size for groceries, for music, the entities differ on versions. The second phase of VARSPOT extracts contrast features from unstructured text. Here we show some of the top contrast features from different domains. We observe that edition and platform are important for software, packet size and flavor for groceries, and for music, the top contrast features correspond to different versions of the track. Coming to quantitative results, we show the F1 and average precision score for Magellan with and without contrast features for the software domain. We observe that our approach, contrastive entity linkage, significantly outperforms the baseline for both duplicates and variations. For more details about our approach and further experimental evaluation, please visit our poster. Thank you.
Hi, and welcome to our talk on the empirical evaluation of pre-training strategies for supervised entity linking. I am Thibault, and this is work with my colleagues Nicholas, Livia, and Tom from Google Research. Our contribution is a full-layer transformer and entity embeddings that achieve state-of-the-art performance on the kernel and AKBC entity disambiguation tasks. The same model also achieves strong results on end-to-end entity linking and entity linking without in-domain data. Through careful evaluation studies, we show the importance of negative candidate selection, of input perturbation, and of context selection. Entity disambiguation maps a specific textual mention to its corresponding entity in a target knowledge base. In this case, we have to distinguish the great basketball player Michael Jordan from the even greater research. Traditionally, entity linking approaches have relied on knowledge bases, complicated modeling, and task-specific and engineered features. More recently, approaches have shown that using BERT and pre-training on Wikipedia entity links is effective. However, these approaches have focused on constructing general-purpose entity representation, building strong zero-shot entity linking systems, and end-to-end entity linking, so that the limits of pre-training for entity disambiguation have not yet been fully explored. We use Wikipedia as our training data, using its hyperlinks as supervision signal. We derive 17 million links for 5.7 million unique entities. Our model is a full-layer transformer where each pen is represented by the concatenation of its start and end word piece. And we project this through a multi-layer perceptor. For entity disambiguation, those spans are provided by the data while we predict them for our end-to-end entity linking results. Finally, we score each potential entity by taking the dot product with the entity embedding. We train our model with cross-entropy loss normalized over a set of candidates. Computing scores over the 6 million entities is expensive. Therefore, we explore methods to define a tractable set of hard negatives, which we describe next. Page candidates are negatives that are the other entities mentioned on the same page. These tend to be semantically, but not lexically related to the target mentioned. Phrase table candidates are the other entries in an alias table for I mentioned. Finally, random entities are added for robustness. In addition, we also explore adding the same input perturbation as BERT. This enables our model to learn that either Michael or Jordan might refer to Michael Jordan. We found that while this input perturbation was helpful, we did not get additional performance benefits from using an auxiliary math language modeling objective. We evaluate our model on two of the most popular supervised entity disambiguation datasets, CONNELL and TAC-KBP. CONNELL is 1,400 densely labeled newswire documents. Its entity set is the whole Wikipedia. We use two different alias tables for this task, the one originally provided with the dataset and the high-precision one used by most state-of-the-art systems. In contrast, TAC-KBP is sparsely labeled and is limited to 850,000 entities. Since the candidate set is much smaller, we do not use an alias table at inference. Moving on to our results. On CONNELL, our model significantly improves on the existing methods. On the high-precision alias table setting, we achieve an error reduction rate of 36%. On TAC-KBP, our full-layer model compares favorably against the 12-layer transformer initialized from BERT. With simple modeling changes, including the addition of a mention prediction layer, we can achieve strong results on entity linking without any task-specific model. Now to our regulations. We find that candidate selection matters, especially without in-domain training data. On CONNELL, using alias table candidates is key, since that is similar to the setup used at evaluation. On TAC-KBP, where we do not use an alias table at evaluation, random candidates are particularly helpful. Closely matching the pre-training setup and evaluation setup is important on this task. Similarly, input noising is helpful, especially without in-domain training data, adding 4 points on CONNELL performance. Finally, we conduct qualitative error analysis, which shows that we are close to the accuracy upper bound on this task. For instance, we believe that our model's prediction is actually valid here. Thanks for listening to our talk.
Hello, everyone. Today, I'll talk about my work on contrastive entity linkage.
Sorry about that. I'm not sure what happened. Let me figure it out.
Hello, everyone. Today, I'll talk about
give me a second, sorry.
We all know that.
Right, let's try again.
relations play a fundamental role in knowledge graphs. Hi everyone, I'm going to present our work on learning relationship entailment with structured and textual information. We all know that relations play a fundamental role in knowledge graphs. However, relations are usually treated as independent. In knowledge graph embedding, each relation is treated as an atomic unit with separate parameters. Also, relation extraction is formulated as a multi-class classification problem where each relation is an independent class. In this paper, we argue that there is in fact relations among relations, or so-called meta-relations that are interesting to study. We focus on a particular type of meta-relation, relation entailment, where existence of one relation can entail the existence of another. Here is an example relation hierarchy from Wikidata, where the parent relation creator has several children relations, and each child relation can entail the parent. There are several potential applications of relation entailment, such as knowledge graph representation learning, relation extraction, and knowledge graph-based question answering. Motivated by this, we move on to the formal definitions. We denote head and tail entities as H and T and relations as R. Each relation is associated with a collection of head and tail entity pairs denoted by CR. We see that a relation R entails a relation R prime if and only if the instances of R are included by R prime. Based on this, we define the problem of predicting relation entailment as a multi-class classification problem, where given relation R, we want to choose its parents R prime from a bunch of candidates. Next, we briefly go through how we create our datasets. Given the relation hierarchy of Wikidata, we started by collecting instances for each relation and downsampling. The next step is relation expansion, where we split leaf relations into more sub-relations based on the type of head and tail entities to make the number of relations larger. Then we run entity linking to detect mentions in Wikipedia articles. The final step is to randomly split each tier of the hierarchy into training, dev, and test. Next, we briefly describe our method. The first method is to use structured information from knowledge graph. We either directly use the embeddings of the relation or aggregate head and tail entity pairs and concatenate them together. The second method is to use textual information. We explore most words in the middle of the entity pairs and shortest dependency paths. Both are treated as a sequence of tokens and pass through CNNs or RNNs to get a final representation. The last is distribution-based method. Instead of representing each relation as a fixed point, we model it as a probability distribution. Given those representations of each relation, we examine two approaches to predict relation entailment. Unsupervised methods are simply using different similarity measurement between child relation R and the potential parent relation R prime. We also tried supervised method, where we concatenate the child relation and parent relation and pass them through a multi-layer perceptron. We conduct experiments on our datasets, which has approximately 500 parent relations. We evaluate our methods using both accuracy and mean reciprocal rank. Here's the results of different unsupervised methods. We can see that entity embeddings performs much better than relation embeddings, which is probably because entity embeddings is more expressive. We also compare across different knowledge graph embeddings, and Trans-C performs the best. And this is the results of supervised methods. We can see that the accuracy of supervised methods is significantly better than unsupervised methods, and using both structured and textual information is better than only using structured information with respect to accuracy at 1 and mean reciprocal rank, indicating that they are complementary to each other. We also perform error analysis. Let's take a look at the last example where the parent is participant connecting events to persons. The goal is to generalize from the training relation performer, which links sounds to artists, to participating teams, which connect sports events to teams. We can see that the semantic gap between the training and testing is pretty large, making this problem a challenging problem that requires high-level abstraction. Both the paper and code can be found in the following links. Thanks for your attention.
Hi everybody, I'm Ali Hürriyetoğlu from Koç University, Istanbul, Turkey. I'm going to introduce our work on creating a cross-context news corpus for protest events to you. This work is done at Koç University with colleagues from there. The aim of this work to create databases of events, protest events, which we say contextual politics, whether these kind of events cause welfare expansion over many countries, especially India, China, South Africa, Argentina, and Brazil, maybe Mexico. We need a good language resource, a high quality corpus that can capture all this variability. By protest, we mean anything you may think as contentious politics, state demonstrations, industrial actions. The critical point here to have the variability across countries like BART and idol immersion are event types, protest types in India. Those are some examples. There are many protest or event databases, but to the best of our knowledge, none of them really consider this cross-context generalizability of their models. So we wanted to start from the language resource creation from the very beginning to capture this variability. So we hope our models will be more generalizable, or it will be a test bed for us. At the end, the aim to have reliable and valid event databases. Our annotation methodology is like use local news sources, get random samples, use active learning, have the internet agreement as high as possible, and correct as many as possible annotation errors like spot checks or semi-automatically train machine learning models and improve it when you see errors. So those are the main tasks. We have that many patches or data from various sources. Sentence count, when we keep the whole document, we annotate all sentences of the document. Total sentence count is like this for 3 batches. For token level, we annotate trigger, place, time, organizer, target, and trigger is the most essential. So if it doesn't occur, the document is not relevant. The cross-context performance, when we train our models and test these models on China or South Africa, is like this. There is a drop in the performance, but we can measure it now. So it is, and we can work on it to improve it. The token level performance is like this. Trigger is quite good because we are optimizing for it. For other types, we tested the FLAIR name and recognition model.
History wasn't sharing for like maybe 2 minutes. Okay. But it looks like an eternity when you
has a good F1 balance point. We release the corpus by sharing the URLs, software, and Docker, and the task is token level. We just share sentences that contain information. We have some targets like multilinguality or checking whether the document contain more than one event, and creating global event database. Please check our shared tasks at CLAY 2019. We used this part of this corpus. We organized a workshop at AREC this year for event sentences, whether they co-referent. So thank you very much for your time. Please contact us and consider to join our email list, so we will be in touch to hopefully progress in this field altogether.
Hi, my name is Derek Tam, and I'll be presenting our work on predicting the hierarchical structures of institutions. This work was done in collaboration with Nicholas Monath and Ari Kobrin and their advisor, Andrew McCallum. Researchers studying science of science often consider questions such as impact of research funding, collaboration methods and networks, incentive structures, and the mobility of researchers. The organizational structure of research institutions plays an important role in this work. For instance, the organizational structure might be important when considering the relationship between the institutions that researchers move between. Similarly, this structure could be informative when studying the distribution of funding across the public universities in a particular state. Many academic, government, and industrial organizations are hierarchically organized. An example of an academic institution hierarchy has a root at the Ohio Department of Higher Education, which is a parent of the University System of Ohio, which in turn is a parent of Bowling Green State University, the Ohio State University, and Miami University. And Ohio State University is a parent of the College of Veterinary Medicine. An example of a government hierarchical organization is rooted at New South Wales government, which has many children and grandchildren. One public database that contains hierarchical structures of institutions is GRID, Global Research Identifier Database, a manually curated database with information about institutions, their locations, and their relationships with other institutions. For example, this is the information it shows about Ohio State University, including its relationships at the bottom. Though GRID contains lots of institutions and their relationships can still be missing. For example, Hunter New England Local Health District is actually a child of New South Wales Department of Health, which is not in GRID. This missing relationship propagates errors such that all the relationships between institutions in the two hierarchies will be missed. To help automate the process of constructing institution hierarchies that can improve databases of institutions such as GRID, we propose a model that will predict whether an institution is a descendant of another institution, such as the missing relationship between Hunter New England Local Health District and New South Wales Department of Health. Our approach for predictions is based solely on the institution name, location, and type. To do so, we model sets of overlapping and non-overlapping tokens with set transformers. Given two strings, the Ohio State University and University System of Ohio, our model first represents each institution as a set of its tokens. Next, we apply several set operations to the original set of tokens. First, we take the intersection of the tokens into two sets. Then we take the set difference of the tokens into two sets. Note that the tokens in University System of Ohio should mostly be in the Ohio State University, since it is its parent. This can be expressed by finding the similarity between University System of Ohio and the intersection of the two. So we add a term that captures their similarity. Next, note that the tokens in the Ohio State University should include extra terms not in University System of Ohio, since the Ohio State University is more fine-grained. This can be expressed by finding the similarity between the Ohio State University and the intersection of the two. So we add a term that captures their similarity. In this case, state is learned to be an important token that distinguishes them. Finally, note that while University System of Ohio should be different from the Ohio State University, it should still have some similarity with the Ohio State University. This can be expressed by finding the similarity between University System of Ohio and what is left in University System of Ohio after moving terms started in the Ohio State University. So we add a term that captures their similarity. We learn to combine these three terms using a linear combination of them as our final score to make predictions. To represent the sets of tokens, we use set transformers without positional embeddings so that they are permutation invariant. The results of our model is shown below. It outperforms other baselines that use different set embedding methods and baselines that use classical deep learning approaches over strings. Several examples that our model is able to score correctly was California State University, Los Angeles. It's a child of the California State University system. And American Institute of Biological Science is a child of the National Academy of Science. In conclusion, we propose a model which predicts parent-child relationships that can be used to form institution hierarchies. Future work includes incorporating the context of institutions or performing set operations in embedding space rather than token space to better capture semantics. Thank you for your time.
Today, I will introduce our work Crossref. This is a collaboration with Lei at BETDANCE and Li Feng at Alibaba. Online news forum has gained increased popularity. How to efficiently navigate through the excessive amount of user comments has become a common issue. For service providers, this trend calls for a better system to categorize the user comments based on important entities that is discussed. For instance, this sample thread compares two prominent soccer players, both named Ronaldo. 3 representative user comments over different groups of entities as selected. This information could help diversify the comments and customize results based on the user interests. The task we just described has been studied in the traditional analytic linking benchmarks. For example, the IDA-Kono dataset. This type of benchmark usually features long documents with formal writing style. However, in online forums, the comment is very short, and there exists a higher degree of irregular naming variation due to informal language. In this work, we propose to mitigate this issue by leveraging the entity information from the associated articles. Existing work on analytic linking relies on rich context for disambiguation, which is usually unavailable for social media domain. Therefore, redundant posts or user information are often leveraged. Most systems target the English language, with a few exceptions using cross-lingual approaches for Chinese. However, none of the above is sufficient for Chinese news comment due to the lack of context, user information, and difficulty in processing emerging entities. So we collect data and conduct our own annotation study. The data format looks like this. The human annotator will first read the article and then a list of comments. The first step is to identify the mention span, and then link them to a knowledge base, which in this work we chose Baidu Baike, which has a better coverage over the emerging celebrities in our dataset. We collect dataset from 2 distinct domains, entertainment and product. But first notice that the comments are very short, with about 20 characters for both domains, while the articles are much longer. For both domains, diverse mention variation exists. For example, the maximum distinct mentions for an entity is over 100 on entertainment domain. Here we show sample mention for both domains. We categorize the mention into different types. The first is canonical names, which are the names entity appear in the knowledge base. For some very popular entities, the knowledge base also registers a list of nicknames. And there exist many other naming variations, such as a short description or even misspellings. Now I will introduce our proposed model. This figure outlines the structure of our system. The left part calculates the mention representation, and the right outlines the entity representation of a given candidate. It will both be transformed to the same space and finally predict a linking probability for the given candidate. We look at the entities from 2 aspects. The first representation is calculated based on the entity-entity co-occur matrix extracted from news headlines. We adopt a node-to-WAC method to calculate the dense representation based on this matrix. For the second part, we run SVD over the entity word co-occur matrix. For mention representation, we first apply a BioSTM network over the common characters, with 1 extra bit in the character embedding to indicate the span of the mention. The base version of the mention representation is then taken as the last hidden state of the LSTM. We also consider a comment attention that learns a weighted sum over all the hidden states of the comment. For the given article, we use string matching to find entities based on their canonical names. We utilize their entity embeddings as described earlier to calculate another bilinear attention to form the third part of the mention representation. In addition to the inner product of the 2 representations, we append a list of hand-picked features to further enhance the model. Finally, in order to improve the robustness of the model, we construct weakly supervised pretraining data by stream matching and pronoun substitutions. We conduct experiments and report accuracy and mean reciprocal ranking scores. We first consider 2 matching-based systems and then a list of learning-based models. Our proposed cross-ref model achieves the best performance in both domains among all the learning-based models and most matching-based systems. We further show updated results. By removing the common attention, the performance drops by almost 6 percentage points in entertainment and 3 for products. If we further remove article attention, the drop would be 13 for entertainment and 10 for the product, indicating the importance of the 2 attention modules. To show the article attention provides meaningful guidance, we compare the prediction results in cases where the attention is correct versus it is wrong, and we observe a strong correlation. When the attention is correct, more than 70% of the predictions are correct. When it is wrong, there is less than 20% is correct. To conclude, we propose Crossref, an analytic linking framework designed for social media news comments. We construct a dataset for Chinese analytic linking study, and our experiments show strong performance over competitive benchmarks.
Hi everybody, I'm Nikita Bhutani and today I'll talk about sample, an unsupervised knowledge-based construction method for opinions and implications. This is a joint work with my colleagues at Megon Labs, including Aaron, Chen, Xiaolan, Behzad, and Wang Qiu. Knowledge bases are everywhere today. A majority of these are built from texts such as on Wikipedia and contain information about real-world entities and their relationships. But there is still tons of information available today in user-written data such as reviews, which is not captured by these existing knowledge bases. And one of the main reasons for that is this information in reviews is typically expressed using opinions and not entities. And also the most frequent relationship between opinions is implication. In this work, we have developed a tool called Sample to build opinion-based knowledge bases from reviews. So what do opinions and implications look like? Opinion is a tuple with a modifier and an aspect. An aspect is the target of an opinion, such as action, characters, writing in movie reviews. A modifier is essentially a phrase that further describes this aspect. This could be fast-paced for action or pretty good for writing. The relationship between opinions is implication. For instance, complex characters could imply pretty good writing. Note that this relationship may not always be expressed explicitly in the same review. And such implication relationships actually have many applications in question answering and retrieval. For example, it could be used to answer a question, show me a movie with good writing, using just the first review, which only talks about complex characters in the movie. There are two limitations of existing knowledge-based construction methods for building such opinion-based knowledge bases. Firstly, they are extractive and not effective at capturing the implication relationship. And secondly, most of them are based on supervised or semi-supervised learning that requires training data for each new domain of reviews. To address these limitations, we have built Sample, which is a domain-independent, unsupervised knowledge-based construction method. And this is how Sample works. Given a corpus of reviews, it first uses rule-based opinion extractor to find opinion tuples, which are then normalized to reduce any surface form variations. Since opinions and implications often do not co-occur in the same review, Sample relies on a matrix factorization technique to summarize signals across multiple reviews. Specifically, it builds a matrix where each row is the item being reviewed, and each column refers to the opinion that is extracted from the review corpus. Each cell then indicates the number of times an opinion is extracted from, is expressed in the reviews of an item. Sample factorizes this matrix and learns embeddings for opinions and items. It then infers the implications between the opinions based on the cosine similarity of their embeddings. The top key implications are then included in the knowledge base. There are many more technical aspects to Sample that we are omitting here in the interest of time. This includes techniques to improve the robustness of the results or interpreting the direction of implications. And we invite you to take a look at the paper to find these technical details. We applied Sample to over 20 domains and closely examined the quality of 6 of the knowledge bases we constructed. We compared against 3 baseline systems, PMI, which essentially captures co-occurrences of opinions. The second baseline was Universal Schema, which also uses the matrix factorization method. And lastly, BERT, which is a strong linguistic baseline for our system. We use mean average precision of the top 5 implications as the metric. And we found that Sample consistently outperformed the baselines on 5 domains except for restaurants. Sample also achieved highest area under the precision recall curve on all domains except for restaurants. And we found that our KV can in fact be used as training data for supervised language model-based methods. We found that it improved the accuracy with a max accuracy of 80%. This indicates that 20% of the implications that are mined by Sample cannot actually be discovered by the language model-based methods. All our tools, scripts, and knowledge bases are publicly available. We encourage you to give it a try. That's all we have. Thank you for listening.
Hello, everyone. It's my honor to present our works on eventuality interment graph construction. I'm Changrong, the first author of this work. This paper is also joint effort with Hongmin, Yangqiu, Wilfried from Hong Kong UST, and Li Feng from Huawei. Here is the outline of my presentation. I would first briefly introduce the recent large-scale eventuality knowledge graph issue and the motivation of enriching issue with the interment relation. After that, I would detailed illustrate our three-step method to efficiently construct the interment graph. Then follows the evaluation results based on human annotation. In the end, I will associate some downstream applications. Okay. As we know, many NLP tasks significantly benefit the large-scale knowledge graphs. Recently, issued a world-centered knowledge graph for the purpose to model knowledge about the activities, states, events, as well as their relations. Here is one such graph sample from Asia. Its eventuality is attracted to match specific linguistic patterns from the dependent parsing tree, and the relation between them are defined by cross relations, such that we extract the relation written from I sleep because I'm tired. It is observed that the current issue is very sparse. In this work, we consider to enrich issue with the interment relation for better eventuality inference. So we summarize the main sparsity of current issue into two aspects: concept transitivity and the verb interment, which is the main motivation of our method. There are several words exploring interment graph construction with different types of nodes. Compared with their words, the eventuality node itself is a dependent graph, including more syntactic rules and contain more complete meaning. Moreover, and the scope of our work, our graph is much huger than the previous ones, which prevent their construction method from directly applying to our settings. And in this work, we propose to build eventuality interment graph with more than 10 million nodes and 103 million edges. Here comes our three-step construction method to overcome the two kinds of sparsity. And we first decompose this eventuality into one predicate, that is the verb, and one argument set, that is mainly composed of nouns. After that, we generate the argument term rules by looking up the existing concept graph properties. For example, we can conceptualize the term apple into two rules. That is, the apple is a fruit, apple is a company. In a similar way, we can also generate the predicate rules from the WordNet, such as tuning. It also entails in eating. On top of the two set of rules, we further use a computational function to compute the local inference score and then take the high confidence pairs. In the end, we conduct the global inference along the predicate inference path. Since the direct transitive clause over the whole graph would bring too many noises. After the global inference step, we can significantly enlarge the generative rules. Here is the evaluation as a result. In order to evaluate of the resulting interment graph, we conduct the human annotation in evident third platform to answer whether the given interment relation between a pair of the eventuality exists. The results show that the global inference step increases the scale of by averagely 3 times. Moreover, the global inference does not lead to heavy drop of the performance, which proves the effectiveness of our methods. Okay, In the end of my presentation, I would also like to point out some potential applications using our internal graph. First, it could be used to generate more reliable common sense knowledge. Second, it's an ideal test bed for some probing tasks. Lastly, it could serve as the external rule base for knowledge reasoning. Our resource and the code are available. If you have any question, you are welcome to ask. Thanks.
Hi everyone, I'm Dhruvesh and I'll be representing joint hierarchies with box embeddings. This work was done with Shep, Michael, Xiang, Luke, and Andrew at UMass. What is a hierarchy? This figure shows an example of a hierarchy. It is composed of nodes related by transitive and asymmetric relation of is-a. For instance, a woman is a person and a person is a mammal. Hence, a woman is a mammal. On the other hand, a cat is a mammal, but not all mammals are cats. Box embeddings are n-dimensional hyperrectangles, which can naturally represent such relations using containment. In this work, we consider two different hierarchies: hypernomy, commonly known as is-a, and meronomy, commonly known as has-part. They form a natural composition with each other. For example, in this figure, a man is a person, and a person has part I. So, a man has part I. This interrelational semantics is used to formulate a joint hierarchy between these two lexical relations, shown by the red arrows in this figure. We introduce a method of modeling these two relations in the same space using two representations for each entity. For example, the green I box represents everything that is a I, while the red has part I box represents everything that has part I. The joint hierarchy, shown on the right, can be represented in this framework as shown by the figure on the left. To elaborate further, a man is a person, hence the green man box is contained within the green person box. Moreover, a person has part I, so the green person box is inside has part I box. This naturally puts the man box inside the has part I box, implying the red edge shown in the figure. To learn the box embeddings, we represent the edges using conditional probabilities. For example, the probability of edge from beta to alpha is given by the ratio of volumes as shown in this figure. The volume of boxes is calculated using the product of side lengths. Here, applying the soft plus to the side lengths ensures that the volume of boxes do not become negative or zero, and it smooths the geometry. Finally, we minimize the binary cross entropy between computed conditional probability using the box model with respect to the ground truth edges of the hierarchy. For the given example graph, this objective encourages the man box to go inside the person box while staying disconnected with the car box. In practice, we observe that many boxes grow disproportionately large when we only use the conditional probability for training. For example, the blue box here need not be so large to contain the smaller 3 boxes. This results in convergence to a suboptimal arrangement of boxes. We thus penalize the volume of a box whenever it exceeds a certain threshold. This form of regularization introduces a global scale on the representation space and helps with the optimization. For our experiments, we use the hypernomy and meronomy hierarchies from BERT. While the hypernym graph is more tree-like, meronomy is less tree-like because it contains a lot of connected components and nodes with multiple pairs. In our first experiment, we explored the extent to which the edges from the transitive closure are necessary to model these individual hierarchies. We supply varying amounts of edges from the transitive closure during training. Here we show the F1 score of binary classification on the unseen test edges with a fixed set of random negatives. In the 0% setting, which is the toughest one, box embeddings do significantly better than other baselines. Even though the performance gap between box embeddings and other baselines decreases with increasing availability of transitive closure edges, the regularized box embeddings always outperform all other baselines. In our second experiment, the objective is to predict the implied edges while jointly modeling the two hierarchies. That is, the green and the purple edges are provided during training, and the model is evaluated on the red edges. We observe that our method outperforms the hyperbolic and multi-relational vector baselines while performing almost at par with order embeddings. The high performance of order embeddings on this task can be attributed to the local nature of the evaluation data. which is created by traversing only 2 steps along the hypernymic hierarchy as shown in the figure. This setup might not be exposing the representation limitations of order embedding, something that is exposed while modeling the relations individually. To conclude, in this work, we showed that far fewer edges from the transitive closure are required for the regularized box embedding model to model a hierarchical graph. We also show that the box embeddings are not restricted to strictly tree-like structures. We proposed a method to model multiple hierarchical relations jointly in a single embedding space. In all cases, our proposed method outperforms or is at par with all the other embeddings.
Hi, I'm Wansok from Naver. I'm going to present about how to build neural semantic parser on the data structure environment. Here is an example of the task. For a given table and question, we want to generate the corresponding SQL query, but with few labels as possible while we are training the model. Because preparing a large amount of logical forms is costly. We built the model based on retrieval method, assuming retrieving partial SQL query would be beneficial by constraining such space. There are several design choices to be considered. For example, which part should be retrieved? And is there any way to reproduce low-cost data set efficiently? Our model named SCAR retrieved synthetic pattern of the logical form from example using the similarity in natural language space. First, the input question is embedded using the transformer-based abstractor, and same goes for the natural language question in examples. And retriever found a logical pattern, and the LSTM-based grounder generated final full SQL query. For example, in question which fruit has yellow color, the retriever found the most close question, which has this logical pattern. Then LSTM grounder generates final SQL query by filling the slot. But since this is a neural model, we need a data set to train the model. Then what would be the best way to prepare the data set under low resource condition? More specifically, what would be an ideal data distribution in the train set? And what can you leverage out of low-cost data set? We use Wikiscope from Salesforce and generate porous subsets of train set and data set and use full test set. We consider 3 different kinds of data distribution. In uniform case, each logical pattern has same amount of example. In random, the data distribution follows the test environment. In hybrid case, it's similar to the random case, but each logical pattern is forced to include minimum amount of example. We also use core question pairs for pre-training, which consists of a pair of sentence and their label, which indicate whether 2 sentences are similar or not. We assume that because we retrieve a logical pattern using the similarity in natural space, the pre-training will be beneficial. Here's the result. Let's focus on this part. Circle-over, one of the state-of-the-art model on Wikiscope task, achieved 49 when it is trained on 900 examples. The other one is SCAR achieved 49, and with the pre-training, it achieved 15. Same trend is observed with other data distribution. But when test environment changes, which could happen on the real service scenario, the model trained with hybrid data set achieved highest performance. Another interesting question, whether can SCAR parse unseen logical pattern even though it is based on retrieval method? And the answer is yes. Upon the inclusion of a new data set without retraining, we observed the accuracy increases. Okay, in summary, we achieved state-of-the-art result on Wikiscope test on the data scarce environment, and that show natural language query similarity data set can be useful for semantic parsing. Careful design of the train set is important, and we found retrieval-based parser can handle unseen new logical pattern. Thanks.
Hello, everyone. Today, I'll talk about my work on contrastive entity linkage. This is
Hi, I'm Wansok.
I think there's one more paper. We find that.
My name is Jun Tai, and today I'm going to present the paper using BibTeX to automatically generate label data for citation field extraction. This is joint work with Chi-Cheng Su, Nicholas Monath, Boris Baseman, and Andrew McCallum. Citation are strings that usually appear in the reference section of a paper and contain information such as title, years, and author names. Given a citation string, the goal is to extract segment fields and tag them with the corresponding labels. Similar to name entity recognition, the citation field extraction is also formulated as a sequence labeling task. The unique feature of this task is its complex constraint between labels. For example, author segment have to be consecutive, and some labels can only appear one per citation, such as years and titles. These constraints vary across domains and disciplines. For example, this picture shows the 3 different citations of the same paper. Given the above challenge, we found that citation field extraction is a useful test bed for sequence labeling problem. It's also an important step in constructing scientific citation graphs such as Cora and WebKB, and also provide useful information for scientific document classification, as well as entity resolution. Due to the nature of the task, it's hard to collect a large-scale human annotated dataset. The only public available dataset has only 2,000 annotated citations, which is not suitable for training and evaluating deep neural networks. Most previous work focused on complex modeling of the input and output sequence. In this work, we hypothesized that straightforward deep neural network can achieve better performance given sufficient amount of training data. Given that collecting human annotated data is costly, we found that to use a noisy auto-generated dataset. Firstly, we propose a simple and reliable data generation process using BibTeX technology. We then ensure that our dataset can be used to improve the performance on a human annotated dataset. We also introduced a new benchmark for the CFA task on the collected data. A citation string can be generated from a given BibTeX entry coupled with a style using the LaTeX compiler as shown in the diagram. BibTeX allows macro stylings that can change the order of citation fields, adding quotes and extra wording. Some citation fields, such as author name, journal, can be abbreviated and reordered as shown in the picture, thus making it difficult to align citation field with their labels. We propose a simple method to recover citation fields label. A reference string is generated alongside with a citation string by injecting special markers. Alignment between citation fields and their labels are resolved by comparing the string and the distance of label segments. We curate a set of BibTeX entries available on the web and generate label citations for them. The resulting dataset, namely the BibTeX CFE, has roughly 41 million label citations with 59 segments labeled. Citation strings have rather different structures than typical sentences. First, pre-trained features on Wikipedia text might not be a good fit here. Since we have sufficient amount of data, we also train a mass language models and use them as a pre-trained features. A standard fine-tuned sequence label models is considered to apply various aspects of model. Notice that we don't use CRF either. We compare the models trained with and without our dataset on the UMass CFE dataset with some standard baseline and the state-of-the-art models. On the left are some application studies. By using the pre-trained features, the deep neural network models already achieve decent F1 after fine-tuning with the UMass train set. Using the feature we train on our data seems to help most the times. Finally, augmenting the big text data and the UMass data gave us the new state-of-the-art on this dataset. We further look at individual labels F1 and include larger scan and loss in table 4, and see only a minor decrease in performance. Having showcased that our big text CFE dataset is useful for human label dataset, we propose a new benchmark on this task as the UMass CFE is fairly small. Overall, our proposed baseline achieved high F1 of 97%. We also provide a domain-specific benchmark for the CFE task. In conclusion, we confirm our hypothesis that better performance can be gained by training deep neural networks with large-scale data. We also release the code data to reproduce the experiment. We leave the task for further improving this task to future work. So this concludes the presentations. We welcome you to check out the complete paper at the provided link. Thank you.
Hi everyone, my name is
All right.
Richard Lin.
Thank you, everyone. So please head on over to the posters. I know we are running about 10 minutes late, but we'll still try to get back here in about 50 minutes and start the next session on time with the invited talks. So yeah, go on over. Just a reminder, there'll be 2 papers per Zoom meeting. So don't get confused if you're thinking they're talking about something else. They still might be talking about the paper you're interested in. All right, see you guys there.
Hey, Andrew.
Hi, Andrew. How are you?
Thanks so much. Very good. I hope you're well also, and your family as well.
Doing our best.
Wonderful. Yeah, thank you for joining us.
Sorry, but you guys are live, just so that you know.
We'll just take one more moment, I believe, while we resolve a technical issue with getting our next speaker set up. Okay, all right. Welcome back, everyone. Andrew, Sue, feel free to begin to present your slides. Everyone, I'm pleased to introduce our next invited speaker, Andrew Su. Like many of us, he works on new methodology for knowledge-based construction, but in addition, he builds real deployed knowledge bases and uses them with focused use cases in mind. I think it's so important for the AKBC community to stay in close contact with actual users of real KBs, so I'm thrilled to have him with us. He is a professor in the Department of Integrative Structural and Computational Biology at the Scripps Research Institute, and he also serves on the Scientific Advisory Board of the Gene Ontology Consortium. He mostly publishes in the field of biomedical research, where he directly engages in making new biomedical scientific discoveries, not only through collaboration with bench scientists, but also through large-scale data mining of knowledge bases, some of which his group builds. For example, his group developed a method to utilize dense genotype maps of inbred mice to do genome-wide association scans for the purpose of identifying novel regulators of biological pathways. And today, he'll speak about building and mining a heterogeneous biomedical knowledge graph. Andrew, welcome. I'll give you a 2-minute warning at about 13 minutes past the hour, so you'll have 5 minutes to answer questions. Take it away.
Fantastic. Thank you, Andrew, and thank you, everyone, for the invitation to come speak. I want to tell you about our experience building and mining knowledge graphs from the biomedical perspective. And to start, I want to describe one particular use case, the use case that we're going to pull throughout this presentation, and that is the one referring to drug repurposing or drug repositioning. So drug repurposing can be summarized in this headline here. Can you teach old drugs new tricks? The basic idea is, can you take existing approved drugs for one disease and discover other diseases for which that drug could also be an effective treatment? Obviously, drug repurposing has become a hot topic given COVID. But even before that, drug repurposing has been something that has been of great interest to the biomedical research community. Not only does repositioning or drug repurposing decrease the time to drug approval, but it also decreases the cost associated with that approval process, and it also decreases the likelihood of failure. So what does drug repurposing mean in the context of knowledge graphs and knowledge bases? I thought I'd run through one particular example that just sort of gives you an intuition about what's going on here. So imatinib is a drug, a cancer drug that was approved in the early 2000s to treat this particular form of leukemia. And the way that works is that imatinib inhibits this protein. It's actually a protein fusion between called BCR-ABL. BCR-ABL is an activator of this particular CML pathway. So the CML pathway is important in the origins of leukemia. And so again, this was all approved in the early 2000s. But there's an interesting other arm behind imatinib, in that imatinib also inhibits another protein called c-KIT. c-KIT is involved in a process called mast cell degranulation. Mast cells are important in some subtypes of asthma. And so based off of this general understanding, the hypothesis is, could imatinib be an effective treatment for asthma? Now, it's worth pointing out that all of the individual edges on the right-hand side of this figure had been worked out for 20 or more years. But it really took a group of researchers at Harvard Medical School to put it all together, propose a randomized controlled trial that they performed in the middle of about 2015 to 2017, and which in fact showed that imatinib could have a positive effect in asthma. So the question is, how do we generalize this task in knowledge-based completion, right? This drug repositioning task, and put together a full pipeline that could do this systematically in a computational drug repositioning pipeline. So there have been a number of people who are interested in this and continue to be interested in this type of work. One paper that was really, inspirational for us was this work published by Daniel Himmelstein when he was a graduate student at UCSF working with Sergio Baronzini. And it's a really nice paper. Let me just first describe the algorithm that they used to uncover these repositioning hypotheses. Essentially, the algorithm called Repetio worked by performing feature extraction based off of metapaths through a knowledge graph. The metapaths being the specific combination of node types and edge types. And then they throw that all into a logistic regression model based off of known drug disease pairs. So certainly we can recognize that this is probably not the state of the art in terms of the knowledge-based completion type of algorithm. In parallel, like we've actually been working with Andrew McCallum's team on applying Minerva and now more recently case-based reasoning. But for the purposes of this talk, we're going to take Repetio, that logistic regression model, as sort of the foundation on which we're going to talk about multiple knowledge bases and think about the knowledge bases underlying these algorithms. This is a visual representation of the knowledge base, or the graph that Daniel used in his work. And it's summarized here. So they integrated data from 29 publicly available resources. It has 47,000 nodes of 11 types. The 11 types are highlighted over here. And 2 million plus relationships of 24 edge types. What's notable, though, is that doing all this data integration is very time consuming, very inefficient to assemble and maintain a knowledge graph like this. And so the question that we were very interested in is what are our alternatives? What can we do to more efficiently automate this type of process? And that's going to be what I'm going to talk about here. There are sort of three arms that we've explored to varying degrees. And the first one is to use a knowledge graph based off of text mining. And here we're leveraging a resource which is called Semantic Medline, or SemMedDB. SemMedDB is an initiative that is run out of the National Library of Medicine. It's based on the SEMREP algorithm, which was first published again in the early 2000s. Again, I think it's fair to say that, or my understanding, I'm not an NLP expert, but my understanding, this is probably no longer the state of the art in information extraction, but there are a few really useful properties about SemMedDB that make us be very interested in how to use SemMedDB. The first one is that they have a nice, robust pipeline for processing all of PubMed abstracts. So they run over all 30 million plus PubMed abstracts every 6 to 12 months, and they have that available for download on the website. And from that, they get 90 million or so odd triples that cover many of the key biological entity types that we care about for drug repurposing, including genes, drugs, diseases, anatomy, so on and so forth. It becomes a nice sort of large graph on which we can perform and test some of our repurposing approaches. Also, it's worth noting, and it's something that we definitely take advantage of, the fact that all triples are anchored to a publication and hence a publication date. So why is that important? Well, initially we thought, okay, well, let's take the Repetio algorithm, let's move it from Daniel's handcrafted heterogeneous network over to SemMedDB, and we'll do something like this, right? So we'll take all known drug disease pairs, probably several thousand of them, and we'll do, they are all approved at a different point in time, right? So the x-axis here is a date, and these triangles are meant to indicate when it was approved for clinical use. We would divide these into a training and a test set, and of course, and that's how we would do our evaluation framework. But of course, if we take all the knowledge available sort of current day, and we're trying to assess how well we would predict these things that have been approved a long time ago, I think it's obvious that we would overestimate our ability to run this in a prospective sense. Right? So then the next thing we tried is, okay, well, let's just, because we have, we can essentially reconstruct our knowledge graph at any point in time by only considering the articles that had been published up to that time, we could essentially set a threshold. We would train on all historical data and then test on all indications that had yet to be approved. And we did that. But what that didn't account for was the difference between indications, drug indications that were just about to be approved versus ones that were further out in the future. And so then we settled on this as sort of our framework. For every drug disease pair, we essentially identified the graph that existed right prior to that approval. And then that's what we used to assess whether or not we could successfully, predict that drug disease indication. And if you do that, where you anchor it right on the year of approval, you get this ROC curve, right? 0 to 1, higher is better. This AUC is somewhere about 0.87. Not surprisingly, if you shift your graph into the future, so again, you're sort of now looking at retrospective prediction, right? Your AUC goes up, and then if you shift your graph to prior to the drug approval, then this is where you are truly looking at a prospective sense, and your AUC goes down. Okay, so if we take all those AUCs and now anchor that, plot that in every year, right? So the 0 is exactly where you're trying to use the knowledge graph at the time of approval and say, can you predict that? This is essentially how that curve diminishes over time. We were looking at the area under an ROC. If you look at also under the precision recall curve, which is more realistic in this sense, given the high number of negatives, you see the same pattern, okay? And so our take home from this analysis was twofold. First, computational drug repositioning is pretty hard, right? Using this algorithm and this knowledge graph, right? We are just not doing great in terms of predicting things in the future, and these are overestimates. We don't actually think this is sort of a bleed through of some signal that gives us sort of this high baseline. We don't think there's actual successes of predicting 20 years in the future. But also we were able to see that we lose almost all of our predictive signal at somewhere around 5 years in the future. So again, it establishes that we have a lot of room for growth. But then what we can do is we can try to identify what the axes are where additional knowledge, additional structured knowledge would have the most impact. And so we do that by looking at specific edges that are in our graph. So for example, compound treats disease. If we now titrate sort of how much knowledge we put in, only data up to 1980, only data up to 1990, only data up to 2000, we can see how that affects the area under the curve, the AUC. And you can see that there's a very strong dependence for compound treats disease edges, that compounds related to compound edges, disease related to disease edges, and anatomy location of disease edges. So this turned out to be a really nice framework, because if you believe that, sort of the historical data might extend in the future, then it suggests that these edge types are the ones that, if we were able to curate more of these would have the greatest impact on our drug repositioning predictions moving forward. Okay, so that's what we did for our text mine network. And we thought that was definitely one area that we continue to work in. The second area that we put a lot of effort into is actually looking at manually curated or crowd curated data. And we do that in the context of Wikidata. So I think there's general appreciation for Wikidata, but just to make sure we're all on the same page, Wikipedia is to text what Wikidata is to data. Denny Ventrashek, who was the founder of the Wikidata initiative, described the mission of Wikidata as providing a database of the world's knowledge that anyone could edit. Our goal, one of our lab's goals, is to sort of commandeer and curate and cultivate the biomedical corner of Wikidata and build out that knowledge graph, that part of the knowledge graph. So there are clearly many analogies to Freebase. I imagine Jamie Taylor could pontificate for hours on the relative merits and lessons learned from Freebase versus Wikidata. But nevertheless, right, Wikidata Us was very appealing because it was a community edited and a community maintained knowledge base of very broad scope. So we thought, okay, well, this could be a substrate for us to do our computational drug repositioning. This is sort of the class diagram of what Wikidata looks like as of late last year, and I'll just walk you through it briefly. So we have a box for diseases. There are about 17,000 diseases that are represented in Wikidata, and these are the items. And we have a list of identifiers by which those diseases are known, and that aids in cross-referencing between multiple databases. Those diseases can be related to genes, so there are over 1 million genes from both human, mouse, and other species there, together with those its identifiers. Those genes in turn could be related to the proteins that they create. These proteins can be related to the medication. So, right, so medications usually work by targeting given proteins. Those medications can be related to pharmacological actions, to chemical compounds, and so on and so forth. So this is just a high-level view of the overall knowledge graph, the biomedical corner of Wikidata that we extracted to do some of our drug repositioning efforts. So, so if we extract this network as is, the first time we did this back in roughly 2017, we again used the Repetio algorithm. We tried to assess how good Wikidata was, and it wasn't very good, to be frank, and that's to some extent to be expected. This straight line here reflects the case where there was no path available between a drug and a disease for which there was a true indication. And so in that sense, they were all scored as 0, and so that's why you have this straight line here. But what we hope to see is an improvement over time, and that in fact is what we saw. So as we now go from 2017 to 2018, you can see an increase in the ROC, and again in 2019, you can see a further jump. And so if we just lay that all out in this stack, you can see that that the performance of Repetio improves over time without any changes to Repetio itself, right? That it's just a property of Wikidata where it is continually improving as the size and the quality of that knowledge base improves, that in turn leads to better and better results in terms of our drug repurposing algorithms. I think in the context of drug repositioning, and as we think about, quote unquote, automated methods of knowledge-based construction, right? I think Wikidata does have some best of both worlds types of properties, right? Because on the one hand, it does happen automatically from the perspective of algorithm developers and data scientists, just because of the community effects, the community curation of all of this knowledge graph. And on the other hand, it is also the output of human curation, right? It's not a text-mined resource. So it's simply the aggregated efforts of many individuals. So we like this balance in Wikidata between these two these factors. So the last type that of knowledge base that we think about is represented on the far right here, and these are what I'll term distributed knowledge graphs. And I'll say this is sort of the newest initiative that we've been thinking about in the context of drug repurposing. And to be frank here, I mean, I actually don't think that Repetio would be applicable here. And so this is more of throwing this out to this community who may have useful thoughts on whether and how we would do machine learning and knowledge-based completion in the context of a distributed knowledge graph. So what am I referring to as a distributed knowledge graph here? Well, in the biomedical space, data federation is very common, right? And oftentimes it is. So oftentimes it's data silos that isn't productive, and it's just due to the fact that people haven't done the work of data integration and aligning data models and things like that. But sometimes data federation is necessary, and I just want to run through a couple examples of why that might be, right? So on the one hand, you might have resources that look at gene correlation matrices. So if you wanted to compare the expression pattern of each gene with all other genes, and you want to do that comparison in the context of not one sample, but hundreds or thousands of conditions, then obviously you get to a very large data structure there. And it becomes impractical to move that around. So here's one case where, okay, having a dedicated resource to serve up that type of data might make sense. Oftentimes we have health data where that is something where for privacy rules, we can't be openly sharing that database. And so there are researchers and tool developers who expose APIs on top of that data that can present summarized data that is useful for the outside world, but doesn't break those privacy rules. And then in yet other cases, we have differences in licensing restrictions. And this reusable data project is a nice example of a metadatabase that tries to categorize resources by their licensing terms. And so anyway, in many cases, redistribution is not allowed. And so then your only hope is to access these through APIs. So if we take for a second the idea that to some extent data federation is necessary, then the question is, well, how do we harness sort of this ecosystem of biomedical APIs in a semantically coherent way? So as one approach to this, there are many other approaches, but as one approach that my group has been involved in is essentially this SMART API initiative. SMART API is an extension of the Open API standard, a standard to describe APIs. The extension is really about semantically precise mappings of both the inputs and the outputs. So essentially you could reconstruct based off of sequential API calls a mini knowledge graph. And the interconnectedness between those APIs is sort of summarized here. So in yellow are the semantic types of the things we might care about. Again, genes, drugs, diseases, variants, pathways, so on and so forth. The edges between them are mediated by biomedical APIs, which are shown at the bottom. And so there are some APIs that mediate links between genes and diseases, others between diseases and chemical substances, and so on and so forth. So now, obviously, if your goal was to generate one massive knowledge graph, you would not want to go through and query these things by their API, right? But again, in cases where you can't do that massive centralization, right, how do we actually put this all together in a way to construct mini knowledge graphs around areas of specific interest? We develop a system. So here's one example query, for example. Suppose you wanted to say that I was interested in Parkinson's disease, and I think there are proteins connected to Parkinson's disease that may have approved drugs. So this is a pretty simplistic example, but you can easily imagine how this type of metapath or this type of query would grow. So we developed a client called BioThings Explorer, and this is a Python library, and essentially allows us to navigate that API map to essentially execute each stage of this. So if the first step is going from Parkinson's disease to related proteins, BioThings Explorer consults that Smart API registry, finds that there is this number of APIs, each of which would return some number of hits to get a total of some number of proteins at this stage from many different resources. And from there, we can consult a number of other APIs that relate those particular proteins to then approved drugs, right? So here we don't have a massive knowledge graph with millions of edges. We have a more focused knowledge graph of tens of thousands, maybe hundreds of thousands of edges. Going back to our example of imatinib to asthma, right? So essentially, this could be a query template that we put into BioThings Explorer that would query this this cloud of biomedical APIs, and then we'll get out again a focused network around this particular question. And the key sort of unknown for us is that, you know, how do we think about ranking all the diseases that come out when you search for imatinib along this type of meta path? And is this amenable to sort of a knowledge-based completion sort of framework? Okay, I've got a few more minutes, so I want to run through one last thing that sort of I think is useful, that might be of interest to this crowd, right? When we interact with clinicians or drug discovery scientists who then would be tasked with validating any prediction that we make, evidence is hugely important, right? If I told somebody that, oh, you know, my black box algorithm said that imatinib could be used for asthma, without any of the underlying rationale, you know, that's not going to get very much traction very quickly. These reasoning chains through the knowledge graph become very important. And what we found in all of our work is that because the biological networks are highly interconnected, right? Very low overall diameter of the graph, you could find many ways in which things can be interconnected. And so pulling out the quote unquote true mechanistic path out of the background of many possible paths has always been a challenge in how we interact with domain experts. And so we did a little bit of work creating what we call a drug MechDB, which is a database of drug mechanisms, where instead of just saying, okay, well, imatinib treats leukemia or imatinib treats asthma, you know, we really walk through the reasoning chain and store this in a computable form. We think this is important because for two reasons. First, it allows us to identify missing or underpopulated edge types in the knowledge graph. And secondly, because we think it's useful as a training data if the output really is to come up with this particular reasoning chain, not just sort of the pair between that and that. So far, drug MechDB, we've curated a ballpark 100 and wrapping up now 120 or so of these examples, and I think we're interested in expanding that more. Okay, so with that, it only leaves me to thank all the people who have been involved. You see Mike Myers, who was a just graduated PhD student who's led a lot of the work in terms of SemNDB and Wikidata, as well as drug MechDB. And then this work was done in collaboration with Chinli Wu, who's another professor here at Scripps, and Kevin, who we jointly supervise. So with that, I'm happy to take any questions.
All right, Andrew, thank you very much. Yes, you have a number of questions, and I'll jump straight into those. You mentioned 11 entity types and 24 relation types. The questioner is wondering, is that enough? Could there be better scientific discovery with more types? And what might be the barriers or the challenges in getting those more types?
I think more is better. There's little doubt of that. But I do think there's diminishing returns, right? You know, there is a dearth of resources. So for example, let me just say this, right? We have proteins, we have genes. Genes produce proteins, right? That's good first approximation. But proteins are also not uniform things. They get decorated with all sorts of post-translational modifications. And each one of those has its own distinct function or interacts with their own set of other protein binding partners. We just don't have a lot of knowledge resources in biology that that describe those more granular interactions in large scale. And so right now, I think that we're at the sweet spot of 12 or 20 sort of node and entity types. I think there's a lot to be gained just from a network on that level of granularity.
Yeah, yeah. Picking up actually one of the comments you were making at the end of your talk, you could imagine that the extra types could be helpful for making better predictions. They could also be helpful for making the predictions more explainable, and that those could be separate questions.
Absolutely.
All right, next question. Let's see, maybe I'm looking at the sorting. Ah, yes, okay. How do you verify the quality of Wikidata as a knowledge graph for medical applications? And it may be adversarial edited to give wrong results.
So we have not seen evidence of vandalism in the same way that Wikipedia is subject to vandalism. So we just haven't seen that. I mean, I think the vast majority of editors there are good faith editors. But assessing quality is something that is really important, the general principle. One of the design principles behind Wikidata is that it's not essentially, it's a database of assertions, right? So it's not there to adjudicate truth. And I think that's an important distinction because there are many disagreements within biology, right? Gene A activates protein B. Well, another group could say, no, that actually doesn't exist. It doesn't happen. And it could be anything from slightly different conditions to context to all this stuff. And so in any case, Wikidata is there to capture assertions that have been made. So we mainly focus on whether or not Wikidata is appropriately capturing the assertion that has been stated in the literature or has been stated in the source database that we're trying to import. And there are various initiatives to make that more robust so people don't think that we've imported a data set, but then somebody changes it, right? We want to make sure there's some sort of hash that establishes the veracity of that. That's a Wikidata initiative.
Yeah, I'll toss in the next question actually, because it's related, I think. So have you done bio-KB error sensitivity analysis? Like, is this drug repurposing inference robust to small errors in KB facts? Or perhaps I could imagine maybe the inference is already so difficult and weak that maybe it's even hard to tell what the effects of errors might be.
We did do a little bit, but the details of it, it didn't, we did that by essentially throwing in noise of random, along random edge types, random edges of given edge types. I don't actually recall that ended up being very productive, but it's a great idea. The general idea of looking at how sensitive we are to random perturbations, something that we still need to explore more.
Yeah. Okay. All right, next. Wikidata contains many relations from biomedical KBs. What's the overlap and how much more effective is using Wikidata for drug repurposing versus other KBs?
I have two answers to that. So first is that by pre-integrating it in Wikidata, we just save a lot of inefficiency, right? If everybody who's doing, creating their own integration of biomedical databases is doing that, there's a lot of data redundancy, there's a lot of redundancy and effort. And so simply by doing it in a community resource, we've just made it, we've done it once, so anybody else can take advantage of it. So that's the first advantage. The second advantage, what was I thinking about? It escapes me. It'll come back, I apologize.
All right. Okay. All right, I think there's time for just one more quick question, or well, actually, maybe not. Actually, I'd see that we've just flipped over the minute and we should go on to the next speaker. Andrew, again, thank you very much.
Thank
you. Glad you're with us. And now for our next speaker, I'll turn things over to Hannah.
Hello, everyone. Diyi, can you please share your slides? Thank you. So I am very pleased to introduce Diyi Yang, our last speaker of today. Diyi is an assistant professor at Georgia Tech. She is an expert in natural language processing and working in different areas, including generation, semantics, and discourse. Most of her work is focused toward applications in social science and health. And today she will talk about her work in this domain. She has received several awards, including Best Paper Award at EMNLP 2015, as well as Best Paper at Sakai 2019. Oh, please go ahead.
Thank you for the wonderful introduction. Hello, everyone. I am Diyi. Today, I'm going to talk about my work on language understanding in social contexts. First, to confirm, can anyone see my slides perfectly?
Yep.
Okay. Okay. So we live in an information age. So as a result, language interaction between individuals is growing exponentially in all sorts of venues. So for example, this number is from a long time ago. There are like 2 billion active Facebook users monthly, and also every second, 6,000 English tweets are being generated. Not only interaction between human and human, interaction between human and agents like bots, robots are also increasing a lot. So given this growing amount of data coming out from communication, we must make sure that our technology can better support and serve human communication in a reasonable and human-like way, not like something funny or machinable. I'm going to show a video here. Some of you may already watched it from my other talks. So see whether it works.
Finally meet you. I haven't been on a blind date in a while. So Doug told me you work in customer service.
That's right. I do the voice recordings for companies such as United Airlines, Blue Cross, and Amtrak.
Wow, Amtrak, huh? Well, then I guess I have talked to you before.
I'm sorry, I didn't get that.
Oh. Would you like to maybe see a movie tonight?
I'd like that. Let me check the movie listings. What movie would you like to see?
Have you seen Flight Plan?
Let me look that up for you. 1 second, please. Here it is. Flight Plan is playing at 7:15, 8:45, 10 o'clock, and 11:15.
Let's do 7:15.
Okay. This is a great date.
Anyway, I just feel...
Okay. We can stop here. So I'm going to share something very different from the other type of research you may see from AKBC so far. So something more around the social. So basically this story tells us that natural language communication contains both content and the social information. So getting the content part correct is not enough, especially if we want to deploy such systems in our real world. There has been a lot of work in our NLP community that focus on natural language, content understanding, and the relatively but growing amount of work on the social part of language. It is impossible to kind of separate the language and the social settings. In other words, the social part here is the foundation where all the language situates. So to better capture the subtle and the complex human behaviors, and its complicated relations with language use, we turn to the systemic functional linguistics here, proposed by Michael Holliday. So basically this provides a social perspective to language study and then view language as a social resource where people use to accomplish their purpose or goals. So basically this studies relationship between language and its functions in social settings. There are multiple meta functions under this framework. And then my work mainly focused on 2 dimensions of it that can be computationally modeled and understood. So the first one is what we call interpersonal semantics. So this one is mainly concerned with speech function, interpersonal relations or social relations. And it involves the understanding of speech acts, emotions, discourse, pragmatics, a lot of interpersonal stuff. The second dimension here is what we call additional semantics. So this meta function looks at the experience of our outer and inner world. So it reflects the context of social process in which the language is used. Thus, we pay more attention to how we use language in the real world and understand how language use reveal our social roles, influence, power, ideology, identity, etc. So as you can see, given the intertwined relations between human behaviors, language use, and social settings, one cannot solve those problems by just using method in one single subject. And there are a lot of challenges that we need to address in order to clearly understand the language use in social contexts. So here, I listed 3 of the no specific order here. So first, as I mentioned, the language use is complicated and also very subtle. As you can see, all the example, phenomena, and the different aspects associated with discourse are pragmatics. Second, most of those scenarios and settings are what I call socially low-resourced settings, where although we have a lot of data, but very limited labeled data to support our understanding of those subtle language use. Third, for many given corpus or contexts, social intelligence or understanding of those social interactions actually goes beyond any fixed corpus. And it's really hard to organize and reason over those social interactions if we want to have both artificial and social intelligence, but we also see some of the recent work on social common sense reasoning. So in today's work, I'm going to quickly use 3 specific examples to go through how we formulate the problems and build the methods to understand the people's language use. Let's first look at how to model persuasive language with limited data. So persuasive communication is everywhere. It shapes our attitude, behaviors, and has been widely used in advertisement, political campaign, or loan request. In this work, we mainly look at how persuasion works in crowdfunding contexts. So we choose Kiva here, which is the largest peer-to-peer lending platform in US, to see whether we can understand the persuasion strategies that people use when advocating for their loan request. Here is one advocacy message from Kiva. So we know that based on the system log that it has persuaded 3 out of 50 people to lend, but why it leads people to give? Instead of building classify here to predict whether a request is going to succeed or not, here we want to figure out what specific strategies in the language that make it persuasive. We are going to answer 3 questions here. First is what type of persuasion strategy there exists. So the NLP community has a lot of work in argumentation where people look at the relational support structures about claims and the relations between them. Persuasion here differs from argumentation since it focuses more on language cues or evidence that shape, reinforce, or change our opinions. So here we use existing persuasion theories in psychology to get our understanding of persuasion strategies. So as Kahneman said in his Nobel Prize winning book, when people are evaluating requests, there are 2 systems going on. System 1 is fast and emotional, so we rely on superficial cues to make decisions. System 2 is slower, more deliberative, and more logic. So we carefully evaluate the request and ask questions like, oh, are those facts correct? We took advantage of this type of theories from psychology to understand the effect of persuasion and basically choose this to get our design of persuasion strategies in language. We further translated those persuasion theories into something that we can mirror in language. So for example, one thing that we found in the corpus a lot is called a scarcity. That is, we value an item more when it becomes rare or urgent. As a result, people try to emphasize the urgency or the scarcity of something, like this loan is going to expire in 35 minutes, please help. We also translated those theories into other conversational acts here, such as emotional language, where people use messages full of emotional violence to make others care and take actions. Or people share their identity, like their group or social identity, because in general, we prefer our own group or identity more over others. We also introduce commitment concreteness and the impact here to capture whether a message talking about providing concrete facts or whether a message emphasizing the broader impact or vision of their loan request. So in a straightforward manner, we can annotate some amount of sentences in those advocacy messages and then train state-of-the-art classifiers to predict the persuasion strategies in each sentence. However, this is time-consuming and expensive. In this work, we want to figure out that whether we can still predict the persuasive acts with limited amount of annotated data that is in a semi-supervised manner here. From a model perspective, we are interested in design models for semi-supervised learning, here more around the sentence prediction, but with document level supervision. So explicitly here, our document level labels are how many people get convinced by a request. And then our sentence level labels are the corresponding persuasion strategy. And this is partially labeled. Semi-supervised setting has been studied for a while, and what I showed here is a classical version of it. So taking our context, for example, a typical setting is that you have limited amount of labeled sentences with their corresponding persuasion strategies and a lot of unlabeled sentences. So in our setting, remember that we also have some global labels at the document level. So to utilize this, we introduce a simple semi-supervised setting here with document level supervision. The intuition is that we want to use the document level labels to supervise the learning of sentence level labels. So similar idea have been already used in computer vision setting where people use image global labels to uncover pixel level labels and bounding box of objects, etc. So straightforwardly, it works we first use a sentence encoder to process each word in a sentence. And then we also introduce a attention mechanism here to learn the informative words and of each sentence. So here we make assumption that each sentence only use one type of persuasion strategy. And then we can use the high level representation of each sentence to predict this latent variable. After getting the sentence vector representation, we can get the document vector in a similar way. So we also introduce a attention mechanism here to measure the importance of each sentence and its persuasion strategy. So taking into account both the sentence level prediction and the document level persuasive label regression together, we come to our final semi-supervised objective here, which includes two parts. So the first part is a loss associated with the sentence classification, and then also the loss associated with the overall persuasiveness regression. We collaborated with Kiva and then used the 42,000 advocacy messages. So here we also call it documents from Kiva. We annotated 3,000 sentences with their corresponding persuasion strategies on Amazon Counter. So as we can see, compared to sentence-only baselines, no matter traditional model or like neural networks, or even like a fully supervised versions, this semi-supervised framework with supervision from the global documents gives a much better performance here in terms of both the sentence level prediction and also the document level task. So with this type of models, we then can apply it to all the messages in our corpus and try to understand what's happening in this domain. So we visualize how important each persuasion strategy correlated with the request success through a linear regression model here. And then we look at the effects of each persuasion strategy on the success of each message. We also control for a lot of other confounding variables in this context. We found that if people mentioning shared identity, like coming from same school or coming from same location, expressing concrete details in the message can help your request fulfilled. But if people mentioning the limited amount of time, it usually does not work well for Kiva. Part of the reason is that if it's going to expire in 20 minutes, then maybe not many people will have time to see that request. We further applied our persuasion strategy classifier to another context called random acts of pizza, where the goal is to write a text message to request and give away free pizzas to strangers on Reddit. As you can see from this example, we found that in this context, concreteness, emotional, and scarcity are the top 3 most important strategies to convince people to give you free pizza. So taking together those 2 experiments, we found that those persuasion strategies are differentially effective for different contexts. It is not that one is always right or good. It's more about using it for a proper context. So to sum up, in this part, we describe a set of theory-informed persuasion strategies, also introduced a method with limited supervision for modeling persuasive language. So we focus on persuasive language here, but there are also lots of other similar socially low resource settings, such as politeness, humor, or other form of subtle social interactions. As mentioned earlier, most of them have limited labeled data. So from a method perspective, how could we develop a relatively generic framework for classification for those social domains, even with limited data? So our recent work introduced a technique called T-mix, text mix here. Basically, it performs linear interpolation in text hidden space to create a lot of augmented training data. So what you can see on the left is the overview of our T-mix. So how it works, first for any given sentence X here, we first randomly sample another sentence, and then we encode them separately in the lower layers using any multi-layer encoder to a layer M. So here we use BERT. Then we can linearly interpolate them after layer M, and then the coefficient lambda here is sampled from the beta distribution here. We then can continue forward parsing in the upper layers using these mixed representations. We assume that the labels for those mixed sentences should also be the interpolation of the original sentence as well. During the training, we can then minimize the KL divergence between those mixed labels and then the probability from the classifier as a supervised loss. So based on T-mix, we further propose this what we call mixed text, a semi-supervised framework for text classification. The core idea here is to leverage T-mix on both labeled and unlabeled data. So I will explain each component quickly. So the first component, we are going to perform augmentations on unlabeled data to generate a paraphrase. So the main intuition is that we expect the model to predict consistent labels for different augmentations. Then we can use the current classifier to predict the class label of them. After getting the predictions of the original sentences and also the augmented sentences, we then perform a weighted average to aggregate those predicted results for as the guessed labels for those unlabeled sentences. To avoid the guessed labels being too uniform distributed here, we adopt a sharpening function to make our predictions more like a one-hot vector. So, so far we generated those guessed labels for unlabeled sentences. To train the classifier, we also perform T-mix on a merged set of labeled sentences, unlabeled sentences, and also augmented sentences. So through interpolating text in this way, we can imagine that labeled sentences can be mixed with either labeled sentences, unlabeled sentences, etc. So that's the overall framework. In the training, in practice, we utilize a KL divergence on the labeled data point. So that's our supervision loss. For unlabeled data point is actually a form of consistent loss. We also introduce the entropy minimization here to encourage our models to produce confident labels on unlabeled data point. So I'm not going to introduce details here. I highly encourage you to check out our mixed text work at the ACL 2020 in 2 weeks. So far we focused on how to help loan advocates to write more persuasive messages by highlighting different persuasion strategies. But what if there are some unwanted framing? In a recent work with my collaborators, we look at the inappropriate subjectivity in Wikipedia, called the framing bias, as an example to better understand the complex and the subtle language behavior here. So again, quick background here. So based on a recent Gallup survey, overall, US adults estimate that over 62% of the news they read in newspapers, see on television, or hear on the radio is biased. And they are even more critical when the news appear on social media. They believe that 80% of them is biased. From a language perspective, so what makes some texts look like biased and another neutral? So if we read those two headlines here, John McCain exposed as an agent of the Rothschild versus McCain accused of accepting inappropriate donation from Rothschild. We feel like the second one is more neutral here. So how could we automatically suggest less biased alternatives to the same text? So let's get a little bit concrete here. So what do we mean by bias? There are many different definitions. So here, what we call bias is actually subjectivity bias. So this is introduced in terms of inappropriate subjectivity, which means that some subjective biased text may involve like subjective attitude, use presuppositions, or casting doubt. So for example, the two headlines we read just now, it's actually biased in two ways. So first is the usage of the word exposed, and then the second is a description of the agent of Rothschild. So here, as I mentioned, our job is to, as an initial effort, we want to deal with this subjectivity bias. And then although the agent of Rothschild also carries some prejudice, so we haven't deal with that in this specific work. So building on prior work, we also found that there are three types of biases in encyclopedia or textbook. So the first one is what we call framing bias. It refers to using subjective words or phrase linked with a particular point of view. So here, most of the gameplay is pilfered from. The second is epistemological bias. So it means that linguistic features that subtly modify the believability of a proposition here, such as developing a new downtown will bring back our arts. The last bias type here is what we call demographic bias. These are the presuppositions of particular gender, race, or other attributes, such as a lead programmer usually spends his career here. So the main goal of our work here is that how could we remove such subjectivity bias from a sentence and to further neutralize that sentence. So instead of pilfered from, we want to see based on, instead of will bring back, we want to see which is promoter's hope will bring back, his career versus their career. We utilize Wikipedia here to construct a parallel corpus. Since editors on encyclopedia and textbooks, they try to avoid a biased language. So specifically, we use this neutral point of view policy, which requires that all content must be written in a fairly propositionally without any editorial bias here. So specifically, so if an editor is making an edit on Wikipedia, and then if he or she notices there is a bias statement, the editor will change it. And then when he or she submit this edit, you can also provide explanation of for what purpose you did this. So we basically use their comments as the ground truth to see whether editors mark this as a neutral point of view or not. And then this is how we get our parallel corpus. So we mainly look at the English Wikipedia and then introduce a very large-scale parallel corpus of biased language with over 180,000 sentence pairs. So here I show some of them. So you can see the text with subjective bias and also their corresponding neutral point of view. So based on this corpus, we also introduced the two baseline models here. So the first is what we call concurrent, which use a simple encoder-decoder framework. We use the BERT as an encoder to process the input text, and then the decoder is attentional LSTM with copy mechanism. We also pre-train our decoder as a language model of neutral text using the neutral portion of our corpus because this will enable us to have a very nice data-driven prior of how neutral target sentences should read like. Specifically, we also add a token-weighted loss here to better model the neutralization process. So again, the intuition here is that because the source and target, they have a very high degree of lexicon similarity, but then our goal here is to learn the structure of their difference, not simply copying words into the output. So basically, we introduce a penalty associated with the change here. The second system is very interpretable. We call it a modular. That is, we explicitly model this process through a tagger. So the tagger here will try to predict whether a specific word is biased or not. We then can combine the prediction of these biased words as well as the encoder representation into some joint representation, which will be the input for the decoder stage. So similarly, we decode the sentence and then use the same pre-training and the weighted loss. When we compare those two methods, so you can see there are pros and cons of different architecture design here. So this concurrent, like end-to-end, is straightforward, easy to use, but it's really hard to control what's going on. Versus in the modular network, we can actually control the generation through this kind of tagger, and it's very interpretable. We can also visualize the biased word portion. The drawback is that it's relatively harder to train compared to this end-to-end fashion. Okay, so we also compared this work with a lot of previous studies, such as transformer, seek-to-seek, and then delete, retrieval, and generation work. We evaluated them in terms of both the automatic measures like BLEU and the accuracy. So accuracy here is exact match, as well as meaning and the bias with human annotations. As we can see here, there is no clear winner. Both models achieve good performance in terms of reducing bias, preserving the meaning and the fluency of the original text compared to baselines. As we can see, the modular part does a better job at reducing bias, while the concurrent part appears to be better at preserving the meaning and the fluency of the original text. Again, there is no clear winner, and then that's why we have two different architecture here to visualize what's going on. We further apply the model trained on this corpus on some out-of-domain data sets. As you can see here, this is trained, tested on political books. The original sentence is activists have filed a lawsuit. So our model changed it to critic of it have filed a lawsuit, or critic of it here. We also applied to news headlines. So changing it from Zuckerberg claims Facebook account to Zuckerberg stated Facebook account or says Facebook account. You can also apply it to like campaign speech of present debate. So original sentence is, this includes amazing Americans, like you can see some of the interesting modifications introduced by our model. Okay, so in this part, we introduce a corpus for understanding subjective biased text in language, and also some models to neutralize bias statement. In the last 3 minutes, I'm going to quickly share what are some challenges and the new problems that language understanding need to solve, especially when it comes to a real world scenario. So here I mainly focus on mental health and well-being related context, which is a greater complementary to what Andrew just mentioned about the bell health domain.
Sorry, the 2-minute warning.
Yes. Yeah, almost there. So based on a study like 11 years ago, so around like 28% of internet users have participated in online support groups for medical condition. We can imagine this number goes up dramatically those days. So people use online health communities to talk about their disease and exchange social support, resource, and information. So we call online health support groups, for people who don't know this, those are the platforms where patients and their caregivers gather together to share experience, ask questions, and provide information. So in addition, more and more people also participate in text-based therapy and counseling conversations. Especially those days, we see a dramatic change to these platforms after the pandemic. So again, this is a very typical message in those health-related forums. So when users first get diagnosed or they are looking for some support, they post their content here, and other people will come here to provide information or advice or care. So given such a large amount of users engaging in text-based conversations to look for support and information, again, we need to make sure our technology can better support their communication. So here are a list of potential NLP tasks or problems that could serve for this goal, such as relation extraction, knowledge base specific to this domain, and a lot of the discourse conversational analysis, as well as recommendations, generations, predictions from noisy data. So for example, some of our work like understand the different discourse acts in this context that people use to exchange social support, or different type of roles that they occupy inferred from their language. We also did recommendation systems on those on the left side of American Cancer Survivor Network to connect people who are looking for support with people who are offering support. When you look at the specific thread, we also offer recommendations. So 10 months after the deployment was live, so over 11,000 people, like patients and their caregivers, have signed up and are using our interventions, which is leading to real-world benefits. So there are more that language technologies can be used to better support people's health-related communications online. And I hope those studies may give you some examples of how and what new NLP problems or methods can be developed for good health. So to sum up, so I mainly talk about the 3 lines of research here as examples of how to understanding language in social contexts. With that, I'd like to conclude my talk and also thank all my collaborators. Thank you for listening.
Thanks a lot for the great talk. So we have a few minutes for questions. I'm gonna read them from a Slido. So the first question, how do you identify biases at the first place? Do you do automatically?
Yeah, so we utilize Wikipedia. So basically, because there is this policy on Wikipedia that says that every content, like piece of information written on Wikipedia, should follow this neutral point of view. That is, all the content should be written in a relatively neutral way. So this is like our ground truth. So whenever an editor insert a statement there and others look like look at a sentence and realize, oh, this may be biased or like violates this policy, then they are going to change it. When they change it, they will submit a comment saying something like, I made this edit because I want to remove this bias statement. So that's how we get our like labels. So basically we look at the comments that the people submit and then do regular expression matching to see whether this is about neutral point of view or not. We also did like a small corpus study on 200 of them to see whether they are really like biased or not. I think over 87 of them are actually bias statement.
So I'm gonna read another question. I think we are out of time, but did you notice factuality of a statement getting affected or becoming less precise? Sometimes the paraphrase that, sometimes biased language and facts are not that easy to disentangle.
Yes, this is a great question. So there is some confounding factors here, whether something is fact, whether something is biased, especially related to neutral point of view, right? So on this kind of like a platform, like Wikipedia or textbook or any encyclopedia, so the policy there is that your text should be written in a neutral way. So even it's an opinion or attitude from others, you should report it in a factual way, in a neutral way, like without introducing any editorial bias here, without any presupposition, without any of the like introducing your own like editorial bias there. So also, like if you look at all the discussions going on Wikipedia, sometimes for each statement, especially related to controversial figures, there are discussions around like how we want to write this, and then are there any alternatives that we could use, etc. So yeah, so there is a lot of discussion going on for this. Right now, we choose to use what Wikipedia presents as the neutral version of the statement.
I see. Thanks a lot, Diyi. So there are a few more questions. I'm gonna email them to you. And now I ask the audience to attend the hallway sessions. There is one for each invited speaker, basically. Thank you.
Thank you. Thank you.